Hello there and welcome to Physics with William, where curiosity gets cozy and science takes the scenic route to slumber. Tonight, we are drifting toward one of the strangest objects in the universe, a place so dense, so extreme, and so unwilling to behave like anything familiar, that ordinary matter seems to lose its old identity. We are going to talk about neutron stars, the collapsed hearts of giant stars, where gravity has pressed the remains of a sun into something barely wider than a city, yet heavier than our own star. If that sounds a little much for bedtime, do not worry. We will take it slowly. No rushing through the cosmos, no alarms, no explosions right beside the pillow. Just a careful, quiet journey into a place where the universe becomes very serious about squeezing things. A neutron star is what remains when a massive star reaches the end of its life and can no longer hold itself up. The star collapses inward, the outer layers blast away, and the core is crushed into a sphere of matter so dense that a single spoonful would weigh about as much as a mountain. That is the usual comparison, of course, and it is a good one, although it does raise the practical question of who is bringing a spoon anywhere near a neutron star. Still, it helps the mind reach toward the scale of it. We are used to thinking of matter as something with space inside it. Atoms are mostly empty space. The floor beneath you feels solid, but at the smallest scale it is a loose arrangement of particles held apart by forces. A neutron star is what happens when nature takes much of that empty space away. It is matter without the comfortable gaps, matter pressed until the old rules begin to bend. Before we go any farther, I would love to know where in the world you're listening from tonight. Are you somewhere quiet, with the lights low and the room beginning to cool? Is it late evening for you, or very early morning, or perhaps the middle of a day that has become slightly more cosmic than expected? There is something rather lovely about the idea that people in different places, under different skies, can all think about the same strange object at once. Somewhere above all of us, though far beyond sight, there may be a neutron star spinning in the dark, sending out beams of radiation like a lighthouse that no ship could ever reach. And here we are, on a small, warm planet, trying to imagine what it is like inside. If you find this kind of journey calming, if the thought of distant stars and quiet physics helps your mind settle after a long day, then I would be very grateful if you gave the video a like and maybe subscribed. It helps this little corner of science and sleep find others who might enjoy a gentle wander through the universe. And if tonight's topic keeps you awake for a few extra minutes, I do apologise. Neutron stars are not exactly the universe's softest pillows, but they are fascinating, and perhaps fascination has its own kind of restfulness when we let it arrive slowly. So settle in, let your shoulders drop, and imagine the night sky not as a flat scattering of points, but as a deep, layered place full of stories. Some stars are young and blue, burning fiercely. Some are old and red, swollen and tired. Some have already died, leaving behind white dwarfs, black holes, or these peculiar objects we call neutron stars. They are not stars in the ordinary sense anymore. They do not shine because they are calmly fusing elements in their cores, like our sun. They are stellar remains. They are what is left when the balance between gravity and pressure fails in the most dramatic way. A neutron star is not really alive, but it is not quiet either. It can spin hundreds of times per second. It can carry magnetic fields so strong they twist atoms out of shape. It can quake, crack, flare, cool, pulse, and perhaps hide forms of matter that no laboratory on Earth could ever produce for more than a fleeting instant. The central question tonight is simple to ask, though very difficult to answer. What happens inside a neutron star? Not just on the surface, where gravity is already fierce enough to make ordinary walking a distant fantasy, but deeper down, beneath the crust, beneath the layers of crushed nuclei, beneath the regions where particles crowd together in ways that are almost impossible to picture. What happens when matter is pushed beyond the conditions found in planets, beyond the conditions found in the centres of normal stars, beyond even the atomic structures that make chemistry possible. At what point does matter stop being the matter we know? This is where neutron stars become especially interesting. They sit on the border between the familiar and the unknown. A white dwarf, another kind of stellar remnant, is made mostly of atoms squeezed close together, supported by a quantum pressure that prevents electrons from being packed into the same states. A black hole, at least from the outside, is what happens when collapse goes so far that an event horizon forms and no light can escape. But a neutron star occupies the narrow and astonishing territory between these fates. It has not collapsed into a black hole, at least not yet, but it has collapsed far beyond ordinary matter. It is like the universe stopped one step before complete disappearance and left us a clue. To understand why this matters, think for a moment about something simple, like a piece of bread, a cup of tea, or your own hand resting under a blanket. All of these things are made of atoms. Atoms have nuclei at their centres, made of protons and neutrons, with electrons moving around them in a spread-out quantum cloud. Most of the atom is empty space. If the nucleus were the size of a tiny seed, the electrons would be far away by comparison, and the rest would be open space held in shape by forces. That empty space is one of the reasons the world can be compressed under extreme conditions. Not easily, of course. Your pillow does not suddenly become nuclear matter when you lean on it, which is probably for the best. But under the gravity of a collapsing stellar core, the pressure becomes so intense that atoms cannot remain atoms. Electrons are forced into protons. Protons and electrons combine to form neutrons. The tidy structure of ordinary matter is dismantled, not gently, but by the overwhelming inward pull of gravity. The result is a star made mostly of neutrons, or at least that is the first and simplest description. It is also the reason for the name. But as with many simple descriptions in science, it is only the doorway. Neutron stars are not just balls of neutrons sitting politely in space. They are layered, dynamic, and deeply mysterious. Their outermost surfaces may contain ordinary atomic nuclei, though under conditions far beyond anything we could stand on. Deeper down, those nuclei become more neutron-rich, more distorted, and more crowded. Lower still, they may form strange shapes sometimes described as nuclear pasta, because even physicists, when confronted with the incomprehensible, occasionally reach for dinner vocabulary. There may be sheets, rods, tubes, and tangled structures of nuclear matter, not because anyone has seen them directly, but because theory suggests that competing forces could arrange matter in bizarre shapes before it finally dissolves into a uniform sea. And then there is the core. The core is where confidence becomes quieter. We know a neutron star must be incredibly dense. We know it must obey gravity, quantum mechanics, and nuclear physics. We can observe its mass, its spin, its magnetic field, and sometimes the way it distorts space-time. But the exact state of matter in the deepest interior remains one of the great open questions. Are the neutrons still intact down there, packed together like an unimaginably dense fluid? Do other particles appear, such as hyperons, which are heavier cousins in the family of baryons? Do the neutrons break down into quarks, forming a kind of quark matter where the usual boundaries between particles have dissolved? Could there be something even stranger, a phase of matter that sounds less like astronomy and more like a recipe from a very advanced alien kitchen? We do not yet know. That uncertainty is not a failure. It is part of what makes neutron stars so valuable. They are natural laboratories. They create conditions far beyond the reach of human machines. On Earth, particle accelerators can smash particles together at tremendous energies, and that teaches us a great deal about matter at small scales. But a neutron star does something different. It holds matter under crushing pressure for thousands, millions, even billions of years. It allows nature to ask a question we cannot fully ask in a laboratory. What does matter become when it is forced to remain dense? There is something humbling about that. We often imagine science as a process of mastering the universe, naming things, measuring them, placing them into neat categories, and perhaps arranging them alphabetically if the funding allows. But neutron stars remind us that the universe still keeps rooms we cannot enter. We can look through the windows, infer the furniture, listen to the sounds through the wall, and build careful models of what might be inside. Yet the interior itself remains hidden. No probe will land on a neutron star and send back a postcard saying the crust is lovely this time of year. The surface gravity alone would destroy anything made of ordinary matter. The radiation would be lethal. The magnetic fields near some neutron stars would interfere with chemistry itself. To visit one is not an engineering challenge in the usual sense. It is more like asking how to stroll comfortably through a thunderbolt, and still we study them. We study them because they tell us about death, density, gravity, matter, and the limits of knowledge. We study them because they are connected to some of the most powerful events in the cosmos. When two neutron stars collide, they can send ripples through space-time and forge heavy elements, including gold and platinum. That means the jewellery in a drawer, the metal in a ring, or tiny traces of heavy elements in Earth's crust may have ancient links to collisions between dead stars. It is a strange thought to take to bed, I know. Somewhere in the history of the galaxy, two objects smaller than a city may have spiraled together, merged in a flash, and helped seed the material world around us. The universe is very good at turning catastrophe into ingredients, but tonight we are not starting with the collision. We are starting with the object itself, with the idea of matter being pushed until it changes. The phrase where matter breaks down does not mean matter simply vanishes. It means the categories we usually rely on become less useful. Atoms break down into nuclei and electrons. Nuclei change as protons and electrons merge. Neutrons crowd together until their own behaviour may change. At each deeper level, matter does not become nothing. It becomes something less familiar. The rules do not disappear, but they reveal sides of themselves we do not normally meet. It is rather like discovering that a quiet neighbour who waters the plants every Tuesday also knows how to juggle flaming torches. Same neighbour, very different conditions. The surface of a neutron star is already extreme, but if you could somehow hover above it, safely and impossibly, it might not look like a normal star. Many neutron stars are too dim in visible light to be seen without sensitive instruments, but they can glow in X-rays because they are incredibly hot when young. Some are pulsars, rotating rapidly and sweeping beams of radiation across space. If Earth lies in the path of those beams, we see pulses, regular flashes that can be timed with extraordinary precision. The first pulsars were so regular that scientists briefly wondered whether they might be signals from an intelligent civilization. That is not a foolish thought, really. If the sky suddenly begins tapping at you with the accuracy of a cosmic clock, it is only polite to consider who might be knocking, but the source was natural, a spinning neutron star with beams crossing our line of sight. This regular pulsing gives us one of the ways to study neutron stars. Their rotation tells us about their size, structure, and energy loss. Their sudden glitches, small changes in spin, may reveal interactions between the crust and the superfluid interior. Their radiation can help us estimate their magnetic fields and temperatures. More recently, gravitational wave observations have opened another window. When neutron stars orbit each other and merge, the pattern of the waves they produce carries information about how stiff or soft their matter is. In other words, by listening to the shape of space itself, scientists can learn something about matter under the most intense pressures known outside black holes. That is a sentence that sounds dramatic, even when whispered. Still, the picture remains incomplete. The inside of a neutron star is not a place we can draw with perfect certainty. It is a layered model shaped by observation, mathematics, and careful physical reasoning. We can say what likely happens in broad terms. We can describe the collapse that creates it. We can explore the crust, the outer core, the deeper possibilities. But some of the most important details are still being debated. That is why neutron stars are so alive in modern physics. They are not just old remnants from a completed story. They are active questions. and perhaps that is a good way to approach them tonight, not as a subject to conquer, but as a place to visit carefully with the mind. We will move from the life of a massive star to its final collapse. We will see why the core falls inward and why the outer layers erupt. We will look at how a star larger than the Sun can leave behind something only about the size of a city. We will follow gravity as it squeezes atoms until electrons and protons are forced together. We will pass through the crust, where matter may form strange nuclear shapes, and then descend toward the core, where the known language of particles begins to grow uncertain. Along the way, we will keep one foot in the familiar world, because even the strangest physics is easier to approach when it begins with something human. A kettle boiling, a spoonful of matter, a city at night, a tired listener under a blanket contemplating the fact that somewhere in the galaxy there are stars made of crushed atoms spinning in the dark. For now, let us hold the image gently. A neutron star is not large by astronomical standards. It is not a sprawling nebula, not a galaxy, not a glowing giant that fills a solar system. It is compact, concentrated, a stellar memory pressed into a sphere. Yet inside it, the universe may be testing the deepest rules of matter. It is a place where gravity wins almost completely, but not quite. A place where collapse has gone terribly far, but has paused before becoming a black hole. A place where density turns ordinary particles into something strange, and where the boundary between what we know and what we suspect becomes very thin. So if you are comfortable now, if the room has settled, and the day has loosened its grip a little, we can begin following the story backward to the star that came before. Before the neutron star, there was a massive sun burning through its fuel, holding itself up against gravity by the heat and pressure of nuclear fusion. It shone for millions of years, bright and fierce, spending its life in a delicate balance it could not keep forever. And when that balance finally failed, the collapse began. A massive star spends most of its life doing something that sounds simple. Though it is anything but simple, it holds itself up. That is really the heart of the story. A star is not just a glowing ball sitting peacefully in space like a lantern hung in the dark. It is a constant negotiation between two powerful tendencies. Gravity wants everything to fall inward. Heat and pressure from nuclear fusion push outward. For millions of years, sometimes longer, these two sides keep one another in check. The star shines because its core is hot enough and dense enough to fuse lighter elements into heavier ones, releasing energy that streams outward through layer after layer of gas. That outward flow is what keeps the star from crushing itself. It is a little like a tent held up by warm air, except the tent is larger than planets. The warm air is plasma, and the whole thing is taking place in a furnace that would be rather difficult to fit into a campsite. Our own sun lives this way, quietly by stellar standards, fusing hydrogen into helium in its core. It has enough fuel to continue for billions of years, and it is not massive enough to end as a neutron star. The stars we are interested in tonight are far heavier. They begin life with many times the mass of the Sun. Because they are so massive, their gravity squeezes their cores harder, which makes their interiors hotter, which makes their nuclear reactions run much faster. They are bright, impressive, and rather wasteful. A small red dwarf can sip its fuel for trillions of years, glowing faintly and patiently, like someone making one cup of tea last all afternoon. A massive star burns through its fuel as though it has just discovered there is a sale on sunlight and everything must go. This fast life is important because it sets the stage for the collapse. A giant star is not destroyed because something attacks it from outside. Usually no wandering planet bumps into it. No cosmic hammer comes swinging through space. No villainous comet arrives with a dramatic cape. The crisis begins inside. It begins when the core runs out of the fuel it needs to keep producing enough pressure. During most of the star's life, hydrogen fusion provides the outward support. Hydrogen becomes helium, and that process releases energy. When the hydrogen in the core is mostly used up, the star adjusts. The core contracts, the outer layers expand, and the star can become a red supergiant, swollen and luminous, with a surface so large that if placed where the sun is, it might engulf the orbits of inner planets. Inside that bloated outer envelope, the core becomes hotter. Helium begins to fuse into carbon and oxygen. Later, in the most massive stars, carbon can fuse into heavier elements. Then neon, oxygen, and silicon can burn in turn. This is not burning in the ordinary sense, of course. There is no flame licking around inside the star like a fireplace. It is nuclear fusion, the merging of atomic nuclei under enormous temperature and pressure. But astronomers often use the word burning as shorthand, partly because it is useful, and partly because saying nuclear fusion stage every time is the sort of thing that can make even a supernova feel administratively heavy. As each fuel is exhausted, the core contracts again, heats up again, and begins the next stage if the star is massive enough. These later stages happen faster and faster. Hydrogen burning may last millions of years. Helium burning is shorter, carbon burning shorter still. By the time the core is fusing silicon into iron group elements, the final stage may last only days. Imagine spending most of your life calmly building a house, then doing the last room in a frantic weekend because the universe has become very strict about deadlines. Massive stars are like that near the end. They rush through their final fuels, building layer upon layer inside themselves. The result is often compared to an onion, which is helpful as long as we remember not to picture anything too tidy. The dying star develops shells, with different elements undergoing fusion at different depths. Hydrogen may continue fusing in an outer shell. Helium burns beneath it. Deeper layers process carbon, neon, oxygen, and silicon. At the center grows an iron-rich core. This iron core is the problem. It is not a problem because iron is rare or unstable. Quite the opposite. Iron is strongly bound. It sits near the bottom of the energy valley for nuclear fusion. Lighter elements can release energy by fusing into heavier ones. But once a stellar core reaches iron, fusion no longer provides useful energy. Trying to fuse iron does not help hold the star up. It costs energy rather than releasing it. That is the quiet disaster at the center of the giant star. The core has become something fusion can no longer rescue. For a while, other forms of pressure can resist gravity. Electrons, squeezed into a dense core, provide a kind of quantum support. These electrons resist being packed too closely together, not because they have opinions, but because the rules of quantum mechanics do not allow them all to occupy the same states. This pressure can hold up certain stellar remnants, such as white dwarfs, but in a massive star, the iron core keeps growing. A shell burning adds material to it. Eventually, it becomes too heavy for electron pressure to support. Then the collapse begins. It is hard to say that sentence without making it sound dramatic, because it is dramatic. But the beginning of the collapse is not a long theatrical process. It is sudden. Once support fails, the core falls inward under its own gravity at an enormous speed. Matter that had been held up for ages begins dropping toward the center. The density rises rapidly. Electrons are forced into protons, forming neutrons and releasing neutrinos. This reaction is one of the key steps on the way to a neutron star. Ordinary atomic structure is being dismantled. The particles that once allowed atoms to exist as atoms are being pressed into a new arrangement. The star is not simply shrinking. Its matter is changing identity. The neutrinos released during this process are almost ghost-like particles. They interact very weakly with matter, which means they can pass through huge amounts of material with little trouble. Trillions of them pass through you every second from the sun and other sources, and you do not notice, which is probably just as well. During a core collapse, however, the number of neutrinos produced is staggering. For a brief time, a collapsing star releases more energy in neutrinos than the rest of the visible universe releases in light. Most of them stream away, carrying energy from the core. Some may also help power the explosion that follows, though the details are complex and still an active subject of research. Neutrinos are not just background characters here, they are central messengers of the collapse. As the core falls inward, it reaches densities comparable to those inside atomic nuclei. At that point, matter becomes extremely difficult to compress further. Neutrons are packed close together. The strong nuclear force which acts between particles in nuclei becomes important in resisting further collapse. The inner core stiffens and the infalling material slams into it. This creates a shock wave. You might imagine the collapse as a crowd rushing toward a locked door, only to have the front suddenly stop while everything behind continues forward. The shock begins moving outward through the star, but it loses energy as it pushes through dense material and as it breaks apart heavy nuclei. For a while, in many models, the shock stalls. The star is caught in a furious moment between collapse and explosion. This is one of the great complications of supernova physics. It is tempting to tell the story as if the core collapses, bounces, and the star simply explodes. That is the simple version, and it is not entirely wrong as an outline. But the real mechanism is more subtle. The shock needs help. Neutrinos streaming out from the newly forming neutron star can deposit some of their energy behind the stalled shock. Turbulence, convection, rotation, magnetic fields, and three-dimensional flows all matter. The star does not explode like a perfect spherical firework drawn neatly in a textbook. It is messy, unstable, uneven, and deeply physical. The material boils and churns. Some regions push outward more strongly than others. The explosion is not a clean decision, it is a struggle. When the explosion succeeds, the outer layers of the star are blasted into space. This is the supernova, one of the most powerful visible events in the universe. For days or weeks, a single dying star can shine with the brightness of an entire galaxy. If such an event happens close enough, it can be visible in daylight. Ancient observers recorded sudden guest stars that appeared in the sky and faded over time, some of which were likely supernovae. To someone on Earth, it might look like a new star has been born. In reality, it is the last brilliant display of a massive star destroying its outer body and leaving behind a compact core. There is a strange gentleness in the aftermath once we step back from the violence. The expanding debris becomes a supernova remnant, a glowing cloud enriched with heavy elements. Oxygen, silicon, sulfur, calcium, iron, and many other elements are spread into space. Some were made during the star's life. Some were produced during the explosion itself. Later, this material can mix into interstellar gas, become part of new stars, planets, and perhaps living things. The calcium in bones, the iron in blood, the oxygen in the air, all of these are tied to earlier generations of stars. A massive star dies, and the galaxy inherits its chemistry. This is the universe's recycling program, though admittedly with more radiation and fewer labelled bins. At the centre of the explosion, if the remaining core is not too massive, a neutron star is born. It is extremely hot, newly formed, and incredibly compact. Much of its original rotation is preserved, but because the core has shrunk so dramatically it spins much faster. This is the same basic effect you see when an ice skater pulls in their arms and spins more quickly, except here the skater is a collapsing stellar core and the rink has become a nuclear furnace. A star that once rotated slowly may leave behind a neutron star spinning many times each second. Some newborn neutron stars may spin even faster. Their magnetic fields are also compressed and intensified, sometimes becoming billions or trillions of times stronger than Earth's magnetic field. In some cases, they become magnetars, neutron stars with magnetic fields so extreme that they can produce enormous flares. But before we get too far into the object that remains, it is worth staying a little longer with the death that creates it. The collapse is not just a mechanical squeezing, it is a transformation of scale. A star that once had a core perhaps thousands of kilometers across forms a remnant only around the size of a city. The outer layers fly outward, but the inner core is compressed into matter so dense that our everyday intuition has no useful handle on it. We can compare it to mountains in spoonfuls, or cities with stellar masses, but these are stepping stones for the imagination, not true equivalents. Nothing on Earth is like a neutron star. Even the densest materials in ordinary life are airy by comparison. Lead, gold, uranium, all of them are mostly empty space at the atomic level. A neutron star is what happens when the empty space is no longer allowed to remain empty. The key moment is when electrons and protons combine into neutrons. In ordinary atoms, protons sit in the nucleus, and electrons occupy the surrounding quantum states. Their separation is what gives atoms their size and chemistry. During core collapse, the pressure becomes so great that electrons are driven into protons. Neutrons form in vast numbers. Neutrinos escape. The matter becomes neutron-rich. It is not that every particle instantly becomes a neutron in a perfectly complete way, but the trend is overwhelming. The core is moving from atomic matter toward nuclear matter. It is crossing a boundary that ordinary stars never cross during their stable lives. There is also a limit to what kind of remnant can survive. If the core left behind is too massive, even neutron pressure and nuclear forces cannot halt the collapse. The object continues inward and becomes a black hole. The dividing line is not known with perfect certainty because it depends on the behavior of ultra-dense matter, which is exactly the mystery neutron stars help us study. But broadly speaking, a neutron star exists only if the collapsed core lands in the narrow range where gravity is enormous, yet not quite enough to win completely. That is part of the tension that makes these objects so interesting. They are suspended between survival and total collapse. The supernova itself may also give the neutron star a kick. Because the explosion is uneven, more material may be ejected in one direction than another, and the compact remnant can be shoved the opposite way. Some neutron stars race through space at hundreds of kilometers per second. They are not drifting lazily through the galaxy. They are stellar cannonballs, launched by the asymmetric death of their parent stars. A massive star may have spent its life in a cluster, surrounded by other young stars, only for its remnant to be flung away into the dark. There is something almost impolite about that. After all those millions of years of stellar company, the newborn neutron star leaves at high speed without so much as a forwarding address. For astronomers, these events are not just theoretical. We have observed supernovae. We have detected neutrinos from a nearby supernova in the Large Magellanic Cloud in the 1980s, a major confirmation of core collapse ideas. We have studied supernova remnants such as the Crab Nebula, which contains a pulsar at its centre. That pulsar is a spinning neutron star, the compact leftover from a supernova observed on Earth in the year 1054. The Crab pulsar still beams radiation into space, a ticking remnant inside a glowing cloud. It is one of the clearest examples of how a stellar death can leave behind a compact, energetic object that continues to shape its surroundings long after the explosion fades. The Crab Nebula also reminds us that a supernova is not just a single flash, it leaves structure behind. The expanding gas carries energy, magnetic fields, and newly formed elements. The central neutron star can inject more energy into the remnant through winds of particles and radiation. The whole system evolves. A stellar death becomes a long aftermath. Even after the bright explosion is gone from human skies, the remnant keeps expanding, glowing, and interacting with the surrounding interstellar medium. A star dies quickly at the core, but the consequences spread for thousands of years. Inside the original massive star, the final collapse may take less than a second for the inner core. That is a remarkable thing to consider. A star lives for millions of years, building layers, fusing elements, maintaining balance, and then the central failure unfolds in a blink. The outer envelope does not know immediately what has happened. Information and forces must move through the star, but deep inside the support is gone, and gravity acts with terrifying efficiency. The star's long life narrows into one decisive physical event. Not because the universe is impatient exactly, but because once the conditions cross the threshold, there is no slow alternative. That threshold is the end of hydrostatic balance. While fusion provides pressure, the star can resist gravity. Once the core becomes iron-rich and too massive, pressure support fails. The core collapses, the density rises, the matter transforms, neutrinos flood outward, and the shock attempts to blow the star apart. This sequence is the doorway to the neutron star. It is not a gentle birth, but it is a birth all the same. A neutron star is created in the moment when gravity destroys the old star but fails to erase the core completely. There is a useful way to picture the change without making it too mystical. Imagine a grand old building whose floors have been slowly overloaded. For years the supports hold. More weight is added, then more. The lower levels are reinforced, then reinforced again. At some point, one central support fails, and the entire structure drops inward. But instead of becoming a pile of rubble, the centre is crushed into a new form, a compact block of material unlike the original building. The outer walls blast outward in a cloud of dust. What remains is not simply a smaller version of what came before. It is something with a different internal structure, made under conditions the original building was never meant to endure. That is not a perfect comparison, but it gives the mind somewhere to stand. The death of a giant star is also a reminder that stars are not eternal objects. They are processes. They begin in clouds of gas. They ignite. They spend fuel. They adjust. They age. Their endings depend mainly on mass, with heavier stars taking more violent paths. A low-mass star may fade quietly. A sun-like star will eventually become a white dwarf after shedding its outer layers. A massive star can end in a core collapse supernova, leaving behind a neutron star or a black hole. The night sky may look calm, but it is full of life cycles unfolding at different speeds. Some stars are just beginning, some are in middle age, some are already gone, their lights still travelling. Others have died so violently that their remains are now laboratories for the deepest physics we know. And this is where the story becomes more focused. The giant star's death gives us the neutron star, but the explosion alone does not tell us what the remnant is like. It tells us how it formed, why it is so dense, and why its matter has been transformed. But now we have to look at the object left behind and ask what kind of thing it really is. The numbers are difficult to hold in the mind. A mass greater than the sun, sometimes much greater, packed into a sphere perhaps only 20 or so kilometers across. A surface gravity so strong that mountains cannot rise high in any ordinary sense. A day that may last a fraction of a second. A crust made not of rock, but of atomic nuclei in extreme conditions. Beneath it, matter pressed toward nuclear density, with the possibility of superfluids, superconductors, exotic particles, and perhaps something even more unfamiliar deeper inside. The massive star is gone now. Its outer layers are expanding into space, carrying the chemical record of its life. The bright supernova fades. The surrounding nebula glows, and at the centre sits the remnant, tiny compared with the star that made it, but far more extreme than almost anything else in the universe. A city-sized object with a star's worth of mass, cooling slowly, spinning rapidly, and holding within it the next part of the question. What does gravity do when it has crushed a sun down to the scale of a landscape? What remains after the supernova is almost hard to describe without sounding as though the numbers have gone wrong. A neutron star can contain more mass than the sun, and yet its width may be closer to the size of a large city. Not a planet, not a moon, not even a small country. A city. You could place one over London, New York, Paris, Amsterdam, or Tokyo, at least in imagination, and the object itself would not stretch far beyond the urban landscape. But packed into that modest span is matter heavier than anything our daily experience can prepare us for. It is as though the universe has taken the mass of a star and compressed it into something that could fit inside a morning commute. Although, to be fair, the traffic would be noticeably worse. This is one of the first things to understand about neutron stars. Their strangeness begins with size. Astronomers are used to thinking in large scales. Planets are large. Stars are larger. Nebulae are enormous. Galaxies are so large that even light takes many thousands of years to cross them. But neutron stars are different. They are tiny by astronomical standards. If you were looking across interstellar space with ordinary eyes, even from relatively nearby, you would not see a broad glowing surface like the Sun. You would see nothing at all, unless the neutron star happened to be hot enough, close enough, or beaming radiation in your direction. It's not large enough to dominate the sky by size. It dominates by density, gravity, and the extreme physics hidden inside it. A typical neutron star may be only around 20 to 30 kilometers wide. That is a number we can almost understand, which makes the next part even worse for the imagination. A person could drive that distance in less than an hour under ordinary conditions, assuming the road was clear and the person was not stuck behind a tractor with heroic confidence. The distance from one side of a neutron star to the other is not cosmic in the usual sense. It is familiar. It is the distance between neighborhoods, airports, suburbs, and city centers. Yet the mass inside that space can be greater than the Sun's mass. Our Sun is so massive that it contains almost all the material in the solar system. Jupiter, Saturn, Earth, all the asteroids, all the comets, all the other planets together are only a small leftover compared with the Sun. Now imagine something even heavier than the Sun squeezed down into a ball smaller than many cities. That is the beginning of the neutron star problem. The density follows from this compression, and it is almost beyond language. A sugar cube of neutron star material, if such a thing could exist outside the star, would weigh about as much as a mountain. Sometimes people say a teaspoon would weigh billions of tons. The exact comparison depends on where in the neutron star the material comes from and how one chooses to imagine the impossible act of scooping it. But the basic point is true enough. A very small amount of neutron star matter would have a mass that belongs to something enormous on Earth. Of course, you could not actually place neutron star matter on a table. It would not sit politely beside the biscuits. Without the immense pressure of the star holding it together, it would be unstable in ways that are difficult to describe gently. The table would not appreciate the experiment. Neither would the floor, the building, the continent, or really any nearby geological feature. Density in ordinary life is something we usually experience through materials. Wood floats, stone sinks, metal feels heavy for its size. Lead feels heavier than aluminium. Gold feels heavier still. But these differences are tiny compared with the jump from ordinary matter to neutron star matter. The reason is that ordinary matter, even dense metal, is mostly empty space. Atoms have small nuclei surrounded by electron clouds. The nucleus contains most of the mass, while the atom's size is set by the spread of its electrons. If you compress matter enough to remove most of that atomic spacing, you get something much closer to nuclear density. A neutron star is not just a heavy object. It is an object where matter has been squeezed toward the density of atomic nuclei and then arranged on the scale of a star. That combination is what makes it so unusual. It helps to remember that the star did not simply shrink like a balloon losing air. The matter changed during collapse. In the core of the dying giant star, electrons were forced into protons, forming neutrons and releasing neutrinos. The result was matter rich in neutrons, packed under extraordinary pressure. So when we say a neutron star is dense, we are not talking about normal atoms pressed closer together in a slightly uncomfortable way. We are talking about matter that has lost much of its atomic structure. Chemistry, the familiar science of atoms bonding and sharing electrons, does not really have a comfortable place inside most of a neutron star. You cannot have ordinary rock, ordinary metal, ordinary water, or ordinary gas under those conditions. The material is too compressed, too hot when young, too controlled by nuclear and quantum forces. It is matter in a state that the everyday world never sees. The surface if we can call it a surface, is already strange. A neutron star may have a thin atmosphere, perhaps only centimeters to meters thick, depending on conditions. Beneath that is a crust, but not a crust like Earth's crust. It is not made of granite, basalt, soil, or anything that would welcome a hiking boot. It is made of atomic nuclei and electrons under crushing pressure. The outer crust may still contain nuclei arranged in a solid lattice, something vaguely like a crystal, though the comparison should be handled carefully. Deeper down, the atoms become more and more neutron-rich as pressure rises. Free neutrons begin to appear. Eventually, the distinction between individual nuclei becomes less clear. So even the solid part of a neutron star is not solid in the ordinary sense. It is a quantum nuclear solid, if that phrase can be made sleepy, which is admittedly a challenge. Its gravity is equally difficult to grasp. On Earth, gravity is familiar enough that we barely think about it, unless we drop something fragile or step onto bathroom scales after a holiday. Earth's gravity holds us to the ground, pulls rain from clouds, guides rivers downhill, and gives our bodies a sense of weight. On a neutron star, gravity is not merely stronger, it is crushingly stronger. The surface gravity may be more than 100 billion times Earth's gravity. If you somehow stood on the surface, which you absolutely could not, you would be flattened instantly. That is not an exaggeration for dramatic effect. The forces across your body would be overwhelming. Your atoms themselves would not remain arranged as you. It is one of those destinations best enjoyed from a very safe distance, preferably with a cup of tea and no landing plans. This immense gravity shapes the star's surface. Mountains on Earth can rise kilometers high because rock can support them against Earth's gravity. On a neutron star, gravity is so strong that even very rigid material cannot form tall mountains. Any bump is pulled down sharply. The surface may be extraordinarily smooth by human standards, with mountains perhaps only millimeters or centimeters high, though the exact possibilities depend on the strength and structure of the crust. A centimeter-high mountain on a neutron star may sound unimpressive, until you remember that it can have a mass far beyond a mountain on Earth. It is another case where size and significance stop matching in the usual way. The universe has a habit of making small things alarming when enough density is involved. The gravity also bends light. Around a neutron star, space-time is strongly curved. This means that light leaving the surface does not travel in the simple, straight paths our everyday intuition expects. Some of the light from the far side can bend around toward an observer. In principle, you might be able to see more than half of the surface at once, because the star's gravity redirects the light. That is a strange thought. A neutron star is so compact that it partially shows you around its own edge. It is not a black hole, because light can still escape, but it lives close enough to that regime that relativity becomes essential. Newton's gravity gives a rough starting picture, but Einstein's gravity is needed to describe what happens near such a dense object. This compactness also affects time. A clock on the surface of a neutron star would tick more slowly compared with a clock far away. Not because the clock is faulty, or because the star is being rude, but because strong gravity changes the passage of time. This is gravitational time dilation, and neutron stars provide a much stronger version than anything we experience on Earth. Light leaving the surface loses energy as it climbs out of the gravitational field. Astronomers can sometimes look for this effect in the radiation from neutron stars, because it can shift the light toward longer wavelengths. Even the light seems tired after escaping, and honestly, who could blame it? A neutron star's rotation adds another layer of strangeness. The collapsed core inherits the angular momentum of the original star. As it shrinks, it spins faster. This is not just a minor spin. Some neutron stars rotate many times per second. The fastest known pulsars spin hundreds of times per second. Imagine an object more massive than the Sun, squeezed into the size of a city, turning faster than a kitchen blender. It sounds absurd, but it is real. The only reason it can happen is that the object is so compact and strongly bound by gravity. An ordinary star spinning that fast would tear itself apart. A neutron star is held together by gravity so intense that rapid rotation becomes possible, though there is still a limit. If a neutron star spins too fast, material at the equator could no longer remain bound. The exact limit depends on the star's mass and internal structure, which means rapid rotation gives scientists another way to test what neutron stars are made of. When a neutron star is observed as a pulsar, its rotation becomes a cosmic clock. Beams of radiation sweep through space from near its magnetic poles. If those beams cross Earth, we detect pulses, one after another, with remarkable regularity. Some pulses are so stable that they rival atomic clocks over certain intervals. This is one of the most practical miracles in astronomy. A dead star, born in an explosion, spinning in deep space, can keep time better than many devices humans have built. If the universe has a sense of humour, it is a dry one. It destroys a giant star, crushes its core into nuclear density, and leaves behind something that says tick, tick, tick with astonishing precision. The magnetic fields of neutron stars can be immense. The magnetic field of Earth is useful. It helps guide compasses and shields us from some charged particles from the Sun. The magnetic field of a neutron star can be billions or trillions of times stronger. In magnetars, a special class of neutron star, the field can be even more extreme. These fields are strong enough to affect the behavior of atoms and the movement of charged particles around the star. They can store enormous energy and release it in flares. A magnetar flare can be so powerful that it affects detectors across the solar system. Again, the object producing it may be only city-sized. There is something almost unfair about that. A small object should not be allowed to behave like an entire cosmic weather system, but neutron stars have never shown much interest in our sense of proportion. The temperature of a young neutron star is also enormous. Newly born neutron stars can be incredibly hot, with surfaces emitting X-rays. Over time, they cool, losing energy through neutrinos from the interior and radiation from the surface. Studying this cooling can tell scientists about the matter inside. If the star cools faster or slower than expected, that may reveal something about the particles present in its core, or about whether parts of the interior behave as superfluids or superconductors. So even the fading warmth of a neutron star becomes a clue. It is like listening to a kettle cool down and trying to infer the shape of the kitchen, except the kettle is made of nuclear matter and the kitchen is governed by extreme gravity. Mass is one of the most important measurements. We know some neutron stars have masses around 1.5 times the mass of the Sun. Some are heavier, reaching more than twice the Sun's mass. This matters because the more massive a neutron star is, the more pressure its interior must withstand. Observing very massive neutron stars rules out some models of ultra-dense matter. If a proposed form of matter is too soft, meaning it cannot support enough pressure against gravity, then it could not hold up a neutron star of that mass. In this way, each heavy neutron star is like a challenge to theory. It says, whatever I am made of, it must be strong enough to keep me from collapsing. The universe does not provide an answer key, but it does occasionally leave a very heavy clue spinning in a binary system. Radius is harder to measure, but just as important. The size of a neutron star depends on how matter behaves at extreme density. If the matter is relatively stiff, the star may have a larger radius for a given mass. If the matter is softer, it may be more compact. Modern X-ray observations and gravitational wave detections are helping narrow down these possibilities. When two neutron stars spiral toward each other, their gravity raises tides on one another. The amount of tidal distortion affects the gravitational waves they emit before merging. A stiffer neutron star deforms differently from a softer one. So by measuring ripples in space-time, scientists can learn about the internal resistance of matter at nuclear density. It is a wonderfully indirect method. We cannot open a neutron star, but we can listen to how it squishes. Binary systems are especially useful. Many neutron stars have companion stars, and some orbit other neutron stars. By watching the timing of pulsars in binary systems, astronomers can measure masses with great precision. In some cases, the orbit slowly changes because energy is carried away by gravitational waves. This was one of the early indirect confirmations that gravitational waves exist. Later, direct detections of merging black holes and neutron stars opened a new era. Neutron stars are no longer studied only by their light. They're studied by the motion they imprint on space itself. That sounds grand, but it is also practical. Every new kind of observation gives a different piece of the same hidden object. There is another reason the city-sized nature of a neutron star matters. Because it is small and massive, the escape velocity at its surface is enormous. Escape velocity is the speed needed to leave an object's gravitational pull and not fall back. From Earth, rockets need great speed to reach space, but from a neutron star the required speed is a significant fraction of the speed of light. This means that material falling onto a neutron star releases tremendous energy. If the neutron star has a companion, it can pull gas from that companion. As the gas falls in, it heats up and emits X-rays. These systems are among the brightest X-ray sources in the sky. A neutron star does not need to be large to be powerful. It only needs gravity, compactness, and something unfortunate nearby to fall onto it. Accretion can also change the neutron star's spin. Material falling in from a companion can transfer angular momentum, spinning the neutron star up over time. This is how some millisecond pulsars are thought to form. They are old neutron stars that have been recycled by accretion, spun up until they rotate hundreds of times per second. The phrase recycled pulsar sounds almost environmentally friendly, as if the cosmos has a blue bin for collapsed stellar remnants. The reality is more intense, but the idea is accurate. An old neutron star can be revived as a rapid pulsar by feeding from a companion star. Even dead stars can have second acts. Now, when we call a neutron star a city-sized sun, we should be careful. It is not a sun in the ordinary sense. It is not shining by steady fusion. It is not a warm, central star for a system of planets in the way the sun is for us. It is the remnant of a stellar core, a compact object whose energy comes from heat, rotation, magnetic fields, accretion, and gravitational effects. But the phrase captures the astonishing contrast: stellar mass, city scale, solar weight, urban diameter. That is what the mind keeps circling back to. The neutron star is small enough to imagine on a map, yet massive enough to reshape space-time, bend light, slow clocks, and crush matter into forms unknown on Earth. The idea of surface and interior also becomes less simple than it is for a planet. Earth has an atmosphere, oceans, crust, mantle, and core. These layers are made of matter we can study directly or infer through seismic waves. A neutron star has layers too, but the conditions are so extreme that each layer is governed by physics we can only partly test. The outer crust may have nuclei and electrons. The inner crust may include free neutrons and exotic nuclear structures. The outer core may be mostly neutrons with some protons, electrons, and other particles. The deeper core may contain particles or phases of matter we're still trying to identify. A neutron star is not one uniform ball. It is a compressed world of transitions. Because the object is so compact, the pressure changes enormously over a short distance. On Earth, going deeper into the planet increases pressure, but gradually over thousands of kilometers. In a neutron star, moving inward by a few kilometers can take you through changes in density and composition that have no ordinary counterpart. The entire object is a steep gradient. The outermost layers are already extreme, and the center is something else again. This is why the city scale is not comforting. The star is small enough that a cross-section could fit across a metropolitan area, but each layer represents a different regime of matter. A short imaginary descent becomes a journey through nuclear physics. It is worth pausing with a comparison to a city, because it gives the listener a foothold. Picture a familiar city at night. Streets, buildings, rivers, parks, railway lines, windows lit in rows. Now imagine replacing that entire volume with an object whose gravity would destroy all those structures instantly, whose mass exceeds the sun's, whose surface could spin through space many times each second. The comparison is not meant to make the city seem small. It is meant to show how compact the neutron star is. The scale is human. The physics is not. That contrast is what makes neutron stars such good subjects for wonder. They sit at the edge of what can be pictured. You can understand the size. You cannot comfortably understand the density. Even the shape can become interesting. A non-rotating neutron star would be very close to spherical, because gravity pulls everything inward so strongly. A rapidly rotating neutron star can bulge slightly at the equator, just as Earth does, though under far more extreme conditions. The exact shape affects the star's gravitational field and the radiation we observe. If there are tiny irregularities on the surface or in the crust, they might produce gravitational waves as the star spins, though detecting such continuous waves is extremely difficult. Scientists search for them because they would reveal details about the crust strength and the star's deformation. The smallest mountain on a neutron star may speak through the fabric of space, which is a rather dramatic career for a bump. The crust itself must be strong, perhaps much stronger than any material on Earth. The dense lattice of nuclei combined with extreme pressure may produce a solid with enormous resistance to breaking, but it can break. Neutron stars may experience starquakes, where stresses in the crust are released suddenly. In magnetas, changes in the magnetic field can stress and fracture the crust, producing bursts of high-energy radiation. These events tell us that neutron stars are not perfectly static. They evolve, their crusts shift, their magnetic fields decay and rearrange. Their interiors exchange angular momentum. They cool, spin down, flare, glitch, and interact with surroundings. A neutron star may be a remnant, but it is not inert. Glitches are especially intriguing. Some pulsars suddenly spin a little faster, then gradually settle again. This likely involves the interior, perhaps a superfluid component rotating differently from the crust. In a superfluid, matter can flow without ordinary viscosity. Inside a neutron star, neutrons may form such a state. The details are complex, but the broad idea is that the star's interior and crust can exchange rotational motion in sudden steps. When we time pulsars carefully, these tiny changes appear in the rhythm. A distant pulse arrives just slightly earlier than expected, and from that shift, scientists infer something about the hidden fluid inside a city-sized remnant. It is subtle work. Astronomy often is. The universe rarely hands over secrets in large print. The more we look at neutron stars, the more they become a meeting place for different branches of physics. Gravity, nuclear physics, quantum mechanics, plasma physics, thermodynamics, relativity, and astrophysics all arrive at the same object and try to share the table. This can be awkward, as interdisciplinary dinners sometimes are. Nuclear physicists want to know how matter behaves at high density. Relativists want to know how compactness curves space-time. Astronomers want to measure light, pulses, masses, radii, bursts and mergers. Particle physicists wonder whether exotic particles appear. Each perspective is incomplete alone, but together they build a clearer picture. A neutron star is small, but it is scientifically crowded. And all of this began with the fact that a massive star died and left behind something compact enough to hold its mass in a city-sized volume. That is the bridge from the previous part of the story to the next. The supernova explains the birth. The size and mass explain the extremity. But the true question now becomes what that extremity does to matter itself. We have described the outside features, the gravity, rotation, magnetic field, density and scale. We have stood at a safe imaginary distance and looked at the object as a whole. Now the natural next step is to approach the force responsible for all of it. Gravity is not just a background actor here, It is the sculptor. It compresses, bends, heats, strains, and tests matter until familiar structures fail. To understand why atoms collapse, why the crust forms, why the core may hide unknown phases, we have to follow gravity inward and see how its crushing hand changes everything it touches. Gravity is the reason the neutron star exists at all, and it is also the reason the neutron star is so difficult to understand. In an ordinary star, gravity is always trying to pull matter inward, but it is held back by the pressure created in the hot interior. The star survives because gravity is strong but not unchecked. In a neutron star, that balance has already failed once. The old star could not support its core, the core collapsed, and what remains is a place where gravity has not disappeared, relaxed, or learned moderation. It is still pulling inward with extraordinary force, pressing on every layer of matter, forcing particles closer together, and turning the interior into a test of how much compression the universe can tolerate before one kind of matter becomes another. On Earth, gravity is so familiar that it almost becomes invisible. It is the reason your feet stay on the floor, rain falls downward, rivers flow toward lower ground, and a dropped biscuit makes a small but emotionally significant journey to the carpet. We think of gravity as gentle because we live with a gentle version of it. Earth's gravity is strong enough to shape our bodies and guide the moon around us, but weak enough that we can jump, climb stairs, lift a cup, and complain about carrying groceries. Near a neutron star, gravity is not gentle. It is not background scenery. It is the main event. It is so strong that it changes the behavior of matter, light, and time itself. The surface gravity of a neutron star can be more than 100 billion times stronger than gravity at Earth's surface. That number is easy to say and almost useless to imagine. If you weighed a comfortable 70 kilograms on Earth, near the surface of a neutron star your effective weight would become something beyond any ordinary meaning of the word weight. You would not stand there feeling heavy. You would not stand there at all. The difference in gravitational pull between your head and your feet would stretch and crush you. The atoms in your body would not continue politely as atoms in a human shape. This is one of those cases where science fiction sometimes shows a brave explorer stepping onto an exotic surface, looking around and saying something calm into a helmet microphone. A real neutron star would not allow that scene to reach the second sentence. This crushing gravity comes from compactness. A neutron star is not just massive, it is massive within a very small radius. Gravity depends not only on how much mass an object has, but also on how close you are to that mass. The Sun is massive, but its surface is far from its centre compared with a neutron star. A neutron star takes comparable mass and squeezes it into a sphere only about the width of a city. If you stand near that surface in imagination, you are extremely close to an enormous amount of mass. Gravity there rises to a level that changes every physical process. It pulls matter downward, squeezes the crust, shapes the atmosphere, bends the paths of light, and slows the ticking of clocks relative to faraway observers. It is not just stronger gravity, it is gravity in a regime where our everyday instincts stop being useful. A useful way to think about it is to picture Earth's gravity as a slope. We move around on it easily because the slope is mild. A neutron star's gravity is more like a cliff that has decided cliffs are too gentle and would like to become a vertical commandment. Any loose material near the star falls inward at incredible speed. Gas drawn from a companion star can plunge toward the surface, heating up so violently that it emits high-energy radiation. Dust, rock, plasma, anything ordinary that comes too close is accelerated and transformed. The neutron star does not need flames to be dangerous. Gravity does the work. It turns falling matter into energy with brutal efficiency. This is why neutron stars in binary systems can be so bright in X-rays. If a neutron star orbits a normal companion star, it may pull gas away from that companion. The gas does not usually fall straight down at first. It forms a swirling disk around the neutron star, heating as friction and magnetic effects move material inward. By the time the gas reaches the surface or the magnetic poles, it can be moving at a significant fraction of the speed of light. When it slams down, the energy release is immense. A small amount of matter falling onto a neutron star can produce far more energy than the same amount falling onto an ordinary star. It is the compactness again. Gravity has made the drop deeper. The gas falls through a more extreme gravitational well, and the final impact is correspondingly violent. It is rather like dropping a pebble down a garden well compared with dropping it down a well that reaches halfway to the centre of reality. The second one is going to make more of a splash, assuming reality has plumbing. But gravity does not only act on material outside the star, it presses inward through the star itself. Every layer must support the weight of everything above it. On Earth, pressure increases as you go downward through the atmosphere, the ocean, or the crust. Divers know that water pressure rises with depth. Geologists know that rock deep underground is under tremendous pressure from the weight of rock above. In a neutron star, this idea becomes extreme beyond comfort. The outer layers press down on the deeper layers with such force that atoms are distorted, nuclei are squeezed together, and matter passes through states that have no direct counterpart in ordinary life. The deeper you go, the more severe the compression becomes. At the surface, depending on the star's temperature and history, there may be a very thin atmosphere. It may contain hydrogen, helium, carbon, or heavier elements. But it is not an atmosphere like Earth's. It is shallow, dense, and held close by the star's powerful gravity. A mountain on Earth can rise above the air for kilometers. On a neutron star, gravity pulls everything so tightly inward that the atmosphere may be only a thin skin. Beneath it lies the crust, where nuclei form a solid arrangement under pressure. This crust may be only about a kilometer thick, perhaps somewhat more or less depending on the star, but in that short distance the pressure increases enormously. The entire structure is compact. There is no leisurely descent. A few kilometers inside, a neutron star can take matter through transformations that would require impossible conditions on Earth. Gravity also makes the surface astonishingly smooth. On Earth, mountains rise because rock has strength and gravity is modest enough to allow large structures. On a neutron star, the crust may be extremely strong, but gravity is stronger still. Any tall feature is pulled down. The highest mountains may be tiny by human standards, perhaps no more than small bumps. Yet these bumps could contain huge amounts of mass. The word mountain becomes misleading. A small irregularity on a neutron star may have the mass of an earthly mountain range. It would not look impressive in height, but it would matter greatly in gravity. If such a bump is not perfectly aligned with the star's rotation, it could make the spinning star emit gravitational waves, faint ripples in space-time. Scientists search for these signals because they would reveal how much strain the crust can support before it gives way. This brings us to one of the stranger facts about neutron star gravity. It does not merely hold the star together, it competes with the strength of matter itself. The crust is under enormous stress. As the star spins down over time, its shape may adjust. As magnetic fields shift, they may pull and twist the crust. The crust resists for a while, then may crack. These starquakes are not like earthquakes in scale or cause, though the name is helpful. An earthquake is a release of stress in rock. A starquake is a release of stress in a crust made of dense nuclear matter under gravity that flattens almost everything. In magnetars, such crustal changes may trigger bursts and flares. A tiny shift in the crust of a neutron star can release more energy than enormous geological events on Earth. This is another case where the star's small size is deceptive. The forces involved are huge. Gravity also affects the escape of light. Around Earth, light travels so nearly straight that we can usually ignore gravity's effect except in precise measurements. Around the Sun, gravity bends starlight slightly, a famous confirmation of general relativity. Around a neutron star, the bending is much stronger. Light emitted from the surface can curve as it climbs away. A faraway observer might see parts of the star that would normally be hidden around the edge. The star's own gravity allows it to show more of itself than geometry alone would permit. This matters because astronomers use patterns of radiation from hot spots on neutron stars to estimate their masses and radii. The way light bends around the star changes the pulse shape we observe. In other words, gravity edits the star's appearance before the light reaches us. The neutron star is not only hard to study because it is distant, it is hard to study because it warps the evidence on the way out. Time is affected too. Strong gravity slows time relative to regions farther away. A clock near the surface of a neutron star would tick more slowly than a clock in deep space far from the star. This is not an illusion caused by a bad clock. It is part of how space and time behave in strong gravity. Light escaping the surface loses energy as it climbs out, which shifts its wavelength. This effect can help scientists measure the compactness of the star, though in practice the observations are difficult. The basic idea is clear enough. A neutron star's gravity is so strong that even light and time carry the marks of their struggle to leave. That is a quiet sentence, but it is a remarkable one. Gravity reaches into the rhythm of clocks. Inside the neutron star, gravity's role becomes even more direct. It tries to compress the star further. What stops it? Not heat alone. A young neutron star is incredibly hot, but heat pressure is not the main long-term support. The star is supported by quantum effects and nuclear forces, especially the resistance that appears when neutrons and other particles are packed extremely close together. In ordinary matter, electrons provide much of the structure of atoms. In white dwarfs, electron degeneracy pressure helps support the star against gravity. In neutron stars, electrons have mostly been forced into protons during collapse, making neutrons. Now the support comes from the behavior of neutrons and the forces between particles at nuclear density. It is quantum mechanics standing in gravity's path, which is a fairly bold place for quantum mechanics to stand. The term degeneracy pressure can sound as though the particles have developed poor manners, but it means something precise. Certain particles cannot all occupy the same quantum state. When matter is compressed strongly enough, this rule creates pressure even at very low temperature. It is not like ordinary gas pressure, where particles push outward because they are hot and moving quickly. Degeneracy pressure comes from the quantum nature of matter itself. In a neutron star, this pressure helps resist further collapse, but gravity is so intense that even this support may not be enough if the star becomes too massive. That is why there is a maximum mass for neutron stars. Above that limit, the known forms of pressure cannot hold the object up, and collapse to a black hole becomes unavoidable. The exact value of this limit depends on the uncertain behavior of matter at the highest densities, which is one reason neutron stars are so important to physics. This balance between pressure and gravity is not peaceful. It is stable in many neutron stars, yes, but it is stable under extreme tension. The entire star is like a held note at the edge of what matter can manage. If it gains mass from a companion, gravity increases its demand. If its interior contains exotic particles or quark matter, the pressure response may change. If the matter is too soft, it cannot resist compression enough to support observed heavy neutron stars. If it is stiff, the star may have a larger radius and survive at higher masses. This is not stiffness like a wooden plank. It is the way pressure rises as density increases. Scientists describe this relationship as the equation of state, though we can simply call it the rule book for dense matter. The problem is that the rulebook is partly missing. Neutron stars are helping us reconstruct it. Gravity pushes every particle into this rulebook. Near the outer crust, atoms are squeezed into dense arrangements. Deeper down, electrons are more energetic and nuclei become rich in neutrons. At a certain point, neutrons begin to drip out of nuclei, forming a sea of free neutrons around nuclear clusters. This is called neutron drip, and it is one of the early signs that ordinary atomic structure is failing. Deeper still, the nuclei may deform into strange shapes because of the competition between nuclear attraction and electric repulsion. Gravity is not choosing these shapes directly, like a sculptor carving pasta from a block, but it creates the pressure conditions that make such arrangements favourable. Rods, slabs, tubes, and other structures may appear before matter becomes more uniform. It is a strange thought that the crushing hand of gravity may indirectly produce some of the universe's most peculiar microscopic architecture. The force of gravity also changes what happens when a neutron star rotates. Rotation tries to fling matter outward at the equator. Gravity holds it in. The faster the star spins, the more important this competition becomes. Some neutron stars spin hundreds of times per second. At those speeds, the equator may bulge, and the star's shape depends on the balance between centrifugal effects, pressure, and gravity. If the rotation becomes too fast, matter at the equator could be shed into space, but neutron stars are so compact that the limit is very high. Observing the fastest spinning neutron stars gives clues about their size. A star with too large a radius could not spin at certain speeds without breaking apart. So once again, gravity turns motion into a measurement. In binary neutron stars, gravity becomes a conversation between two compact objects. As they orbit, each raises tides on the other. These are not ocean tides because there are no oceans in the ordinary sense. They are distortions in the shape of the star caused by the companion's gravitational pull. The amount of distortion depends on how easily the star's matter deforms. This is important because when two neutron stars spiral together, they emit gravitational waves. The final pattern of those waves carries information about tidal deformation. If the neutron stars are more easily stretched, the signal changes. If they are more compact and stiff, it changes differently. This is one of the most powerful new ways to study neutron star interiors. Gravity creates the waves, gravity distorts the stars, and the waves travel across the universe carrying the imprint of matter under pressure. When two neutron stars merge, gravity's crushing hand becomes even more dramatic. The orbit tightens, the stars spiral inward, space-time ripples outward. In the final moments, the objects tear at each other, collide, and form either a heavier neutron star, a short-lived remnant, or a black hole, depending on the masses and the dense matter physics involved. Material can be flung into space, where heavy elements form through rapid neutron capture. This is one reason neutron star mergers are linked to the cosmic origin of gold, platinum, and other heavy elements. But even before the collision, the inspiral tells us about gravity and matter. It is as if the stars, under unbearable mutual pull, reveal their internal resistance in the way they fall together. Still, for a single neutron star sitting alone, gravity is relentless but not victorious. That is the key point. The star is not collapsing further, at least not if it remains below the maximum mass and is not disturbed too much. It has found an extreme equilibrium. Gravity presses inward, dense matter pushes back. The star survives because the inward pull and outward resistance match at every layer. This is not a comfortable balance, but it is a real one. A neutron star may persist for millions or billions of years, cooling gradually, spinning down, and fading. It is a collapsed object, but not a failed one. It is a structure held at the boundary between star and black hole. This boundary gives neutron stars their special place in astrophysics. A planet is supported by ordinary material strength and pressure. A normal star is supported by heat from fusion. A white dwarf is supported by electron degeneracy pressure. A neutron star is supported by neutron degeneracy pressure and nuclear interactions, with gravity pressing more strongly than in any stable object we can observe directly. A black hole is what happens when no known pressure can stop collapse. So a neutron star is the last visible stand of matter against gravity. It is the final object that can still have a surface, still emit light from that surface, still reveal something of its internal state, before collapse passes beyond an event horizon. That makes it both a physical object and a limit marker. It tells us how far matter can be pushed while still remaining part of the observable universe. There is also a kind of simplicity in gravity's demand. Gravity does not care what matter prefers. It does not care whether atoms would like to remain atoms, whether electrons enjoy their old arrangement, whether nuclei are comfortable with their neighbours, or whether the crust has had a long day. Gravity pulls. That is its job. Under ordinary conditions, matter has many ways to respond. It can stretch, heat, flow, crack, evaporate, ionize, fuse, or settle. In a neutron star, the options narrow. Compression becomes so intense that matter must reorganize at the deepest level. The star becomes a place where the forces inside particles and between particles decide what can still exist. If you could descend through a neutron star in an impossible protective craft, gravity would define every moment of the journey. At the surface, the pull would already be fatal to ordinary structures. The thin atmosphere would cling tightly. The crust beneath would be compressed into a rigid nuclear lattice. As you move downward, pressure would rise sharply. Nuclei would become more neutron-rich. Free neutrons would appear. Exotic nuclear shapes might form. Deeper still, the matter would become a dense fluid of particles, perhaps with superfluid neutrons and superconducting protons. Near the centre, depending on the star's mass, new particles might appear, or neutrons themselves might give way to quark matter. Gravity does not directly announce these transitions. It simply increases the pressure until the current form of matter is no longer the most stable one. That is what makes the phrase crushing hand useful, as long as we do not take it too literally. Gravity is not a hand, of course. It has no fingers, no palm, and no sinister plan. But it does apply pressure in a way that feels almost purposeful when we follow the consequences. It strips away the familiar. It removes empty space. It forces electrons and protons together. It packs neutrons until their collective quantum behavior supports a star. It bends light and slows time. It flattens mountains and deepens the fall of gas. It turns a stellar remnant into a laboratory where the basic structure of matter is tested. And yet, gravity alone is not the full story. If it were, every sufficiently massive collapsed core would simply continue inward. The reason a neutron star exists is that matter pushes back in ways that are subtle and powerful. The next question is not just how hard gravity squeezes, but what matter does under that squeezing. At first, atoms resist as atoms, then atoms fail. Electrons are driven into protons, neutrons dominate. The old architecture of matter, so reliable in planets, people, water, stone, and air, becomes unsuitable for the conditions. To follow the story inward, we have to watch those familiar structures come apart, not in chaos, but according to the deeper rules of physics that only appear when gravity has pressed matter far beyond the ordinary world. To understand what gravity is really doing inside a neutron star, it helps to begin with the quiet miracle of ordinary matter. Everything around you, the floor, the bed, the walls, the air, the cup beside you, and the body resting there listening, is made of atoms. Atoms are reliable little arrangements, at least under the conditions we usually meet. They give us chemistry, texture, temperature, smell, colour, and the comforting fact that a pillow remains a pillow rather than becoming a cloud of nuclear particles with strong opinions. We trust atoms so completely that we rarely think about them. They are the furniture of the familiar world. But atoms are not solid little marbles. That is the first important thing. An atom is mostly space, with a tiny dense nucleus at the centre and electrons arranged around it in quantum states. The nucleus contains protons and neutrons, which hold almost all the mass. The electrons, much lighter, occupy the region that gives the atom its size. When your hand rests on a table, the atoms in your hand are not truly touching the atoms in the table, in the simple way that two stones touch. The particles and fields resist one another. Electrons do not like being forced into the same states. Electric forces push back. Quantum rules keep matter from simply passing through itself. The feeling of solidity is real to you, of course. No one has ever improved their evening by trying to walk through a wall because atoms are mostly empty space. But the solidity is an effect of forces and quantum rules, not because atoms are packed full like tiny metal balls. This matters because a neutron star is born when those ordinary arrangements are pushed far beyond their comfort. In normal conditions, atoms can survive. In planets, rocks, oceans, clouds, and living cells, atomic structure remains intact. Even in the centre of Earth, where pressure is enormous by human standards, atoms and ions still keep enough of their identity for chemistry and material science to make sense. In the Sun, atoms are stripped of many or all of their electrons, forming plasma, but nuclei and electrons still exist as separate ingredients. The Sun is extreme compared with the kitchen, certainly, but it is not extreme enough to destroy the basic categories of atomic matter. A neutron star is different. In the collapse that creates it, the pressure becomes so great that atoms cannot keep their old architecture. The familiar spaces are squeezed away. Electrons are driven into protons. Nuclei are transformed. Matter is no longer matter as chemistry understands it. Imagine, gently, a grand library filled with shelves, aisles, tables, chairs, lamps and quiet readers. That is ordinary matter. There is structure. There are separations. There are rules about where things go. Now imagine the whole building being squeezed from all sides, not just enough to make the chairs creak, but enough that the aisles vanish, the shelves press together, the books merge into blocks, and the difference between room and corridor stops meaning anything. The library has not become nothing. It has become something else, a dense mass where the old layout is gone. Inside a neutron star, atoms undergo a much more profound version of that loss of layout. The old structure fails and deeper rules take over. The first stage of this transformation begins during the collapse of the giant star core. The core has become iron-rich. Fusion can no longer provide support, and gravity wins the argument that had held the star up for so long. As the core falls inward, density rises quickly. Electrons are packed closer and closer together. In ordinary atoms, electrons occupy states around nuclei. Under extreme compression, these electrons become highly energetic. The pressure from the electrons can resist gravity for a while, but in the massive collapsing core it is not enough. Eventually it becomes energetically favourable for electrons to combine with protons. This process is often called electron capture. A proton and an electron turn into a neutron, and a neutrino is released. That small sentence is one of the great turning points in the story. A proton and an electron become a neutron. The particles that allowed atoms to have their usual identity are being rearranged. The electron, once part of the atom's outer structure, is swallowed into the nucleus in a sense, and the proton changes into a neutron. The atom loses not just its size, but part of the reason it could be an atom at all. Neutrinos stream away in enormous numbers, carrying energy from the collapsing core. They are ghostly particles barely interacting with matter, yet during this event they are produced so abundantly that they become central to the explosion and cooling of the newborn remnant. A star's core under pressure is converting much of its proton and electron content into neutrons. It is not a tidy chemical reaction. It is matter-changing category under the command of gravity. This is why the name neutron star makes sense, although it can also be a little too simple. The object is not made only of neutrons in every layer, as though someone poured a jar of identical particles into space and packed them into a ball. The outer regions still contain nuclei and electrons. The deeper regions may contain protons, electrons, muons, and possibly more exotic particles. But neutrons dominate the story because the collapse strongly favours their formation. The star is neutron-rich to an extraordinary degree. The familiar balance of protons, neutrons, and electrons found in ordinary atoms is gone. Matter has shifted toward a state where neutrons carry much of the mass and pressure support. The collapse of atoms is also the collapse of chemistry. Chemistry depends on electrons and the ways atoms share, trade, and arrange them. It depends on electron shells, bonds, molecular shapes, and energy levels. In a neutron star, especially below the outermost layers, these ideas lose their usual meaning. You cannot have water molecules deep inside a neutron star. You cannot have crystals of salt, strands of DNA, grains of sand or metal in the everyday sense. The pressure is too high. Electrons are not available for ordinary bonding. Nuclei are distorted, packed, and transformed. The old language of chemistry becomes like a map of a town that has been buried under a mountain. It was useful somewhere else. It is not useful here. That can feel unsettling, because atoms are the basis of everything we know. But the deeper lesson is not that matter breaks in a careless way. It is that matter has layers of rules. Chemistry is one layer. Atomic physics is another. Nuclear physics is deeper. Particle physics is deeper still. On Earth, chemistry is often the layer we experience most directly. In a neutron star, gravity pushes matter down through those layers until chemistry is no longer the right description. Then atomic structure is no longer the right description. Then even nuclear structure may begin to change. Matter does not forget because the universe becomes confused. It forgets because the conditions no longer allow the familiar forms to remain stable. One of the most useful examples is the fate of the electron. In ordinary matter, electrons help give atoms size. They are light, mobile, and essential to chemical bonds. In a white dwarf, electrons become the main source of support against gravity. They are packed into a dense state where quantum rules prevent them from all falling into the same arrangement. This electron degeneracy pressure can hold up a white dwarf, as long as the object is not too massive. A neutron star begins where that support has failed. The core is too heavy. Electrons are squeezed so fiercely that many are captured by protons. The electron population does not vanish entirely, but its role changes dramatically. Electrons no longer define large atomic structures. They become part of a dense charge balancing mixture, while neutrons take center stage. The proton changes too. In ordinary nuclei, protons are crucial because their positive charge helps define the element. One proton makes hydrogen, 2 protons make helium, 6 make carbon. The number of protons is the identity card of an atom, but in a neutron star, many protons have been converted into neutrons. The remaining protons are relatively few compared with the neutrons, and they exist under conditions where the usual idea of elements becomes increasingly strained. Near the crust, one can still speak of nuclei with many neutrons and some protons. Deeper inside, even those nuclei may dissolve into a continuous fluid of particles. The identity card has been soaked, folded, and pressed under a mountain until the ink runs. Neutrons are often described as neutral, and that neutrality matters. Protons repel one another electrically because they carry positive charge. Neutrons do not have that electric repulsion. In atomic nuclei, neutrons help hold nuclei together through the strong nuclear force without adding extra electric repulsion. In a neutron star, the abundance of neutrons allows matter to become far denser than ordinary atomic matter. But neutrons are not passive. They obey quantum rules. They interact through nuclear forces. They resist being compressed into the same states. When packed at nuclear densities, they form a strange quantum fluid, and their collective behaviour becomes one of the great questions in dense matter physics. The phrase matter forgets. Its shape is useful because shape itself depends on scale. At the atomic scale, matter has shape because electrons arrange around nuclei, and atoms bond into molecules and solids. At higher pressure, those shapes are stripped away. A molecule has a structure because its atoms can maintain positions relative to each other. But if the pressure rises until atoms are crushed and electrons are forced into protons, a molecule cannot keep its form. There is no tiny version of water hiding deep inside a neutron star, bravely maintaining its angle between hydrogen and oxygen, like a very determined piece of geometry. The conditions are too extreme. The shape is not merely distorted. The ingredients that made the shape possible have changed. As density increases, nuclei themselves begin to lose their independence. In the outer crust, nuclei can still form a lattice, surrounded by electrons. It is an exotic solid, but one where nuclei remain identifiable. Deeper down, the nuclei become more neutron-rich. At a certain density, neutrons begin to leak out of nuclei. This is called neutron drip. The name is slightly odd, almost domestic, as if someone has left a tap running in the basement of physics. But the meaning is important. The nuclei can no longer hold all their neutrons. Free neutrons appear, moving through the crust around the nuclear clusters. Matter is now a mixture of nuclei, electrons, and free neutrons. The atom has collapsed, but the deeper structure is still evolving. Below this region, the competition between forces becomes increasingly strange. The strong nuclear force tends to hold nuclear matter together at short ranges. Electric repulsion between protons pushes charged regions apart. Gravity and pressure keep everything compressed. Under these competing influences, nuclear matter may arrange itself into unusual shapes before becoming uniform. Scientists sometimes call these phases nuclear pasta, because the predicted shapes include rods, slabs, and other structures that remind people, perhaps after a long day in the lab, of spaghetti and lasagna. It is a charming name for a very severe environment. No one is serving dinner there. These structures, if they exist, are made of nuclear matter under crushing pressure, and they may affect how the crust behaves, how heat moves, how neutrinos escape, and how the star responds to stress. This is where matter begins to lose not only atomic shape, but also the clear boundary between nucleus and surroundings. In ordinary matter, a nucleus is a compact object separated from other nuclei by the space occupied by electrons. In the deep crust of a neutron star, nuclear clusters may stretch and merge into extended structures. Free neutrons fill the spaces between them. The distinction between one nucleus and the next becomes less clean. The old picture of separate atoms has long since disappeared, and now even the picture of separate nuclei is becoming uncertain. Matter is becoming a continuous nuclear landscape. Further inward, at the boundary between crust and core, nuclei may dissolve entirely. What remains is often described as a fluid of mostly neutrons, with a smaller number of protons, electrons, and possibly muons. This fluid is not like water, of course. Water is made of molecules, and molecules are impossible here. It is a quantum fluid at densities comparable to and beyond those of atomic nuclei. Neutrons may pair up and form a superfluid, a state that can flow without ordinary internal friction. Protons, though fewer, may form a superconducting component. These are not decorative details. They matter for how the star rotates, cools, and changes over time. They may help explain pulsar glitches, where a spinning neutron star suddenly speeds up slightly. The hidden fluid inside may exchange angular momentum with the crust, producing the tiny timing jumps that astronomers observe. At this point, matter has gone far beyond ordinary shape. It is not solid, liquid, gas, or plasma in the everyday sense. Those categories come from familiar conditions and familiar particles arranged in familiar ways. The inside of a neutron star forces us to use more careful language. The crust may behave like an incredibly strong solid. The core may behave like a quantum liquid. Some components may be superfluid or superconducting. But these are analogies and classifications built from physics, not from kitchen experience. If someone asks whether the inside of a neutron star is solid or liquid, the honest answer is that the question needs unpacking. It depends on where you are, what particles you're describing, and what kind of motion or stress you care about. Matter has not merely chosen one of the common states from school science. It has opened a much stranger menu. One of the deeper questions is what happens at the highest densities near the core. Neutrons themselves are not fundamental particles. They are made of quarks bound together by the strong interaction. Under normal conditions, quarks are confined inside protons and neutrons. You do not find a lone quark sitting on a park bench, quietly reading the newspaper. The strong force does not allow that in ordinary circumstances, but in the deepest regions of massive neutron stars, the density may become so high that the boundaries between neutrons begin to overlap. Some theories suggest that matter may transition into quark matter. where quarks are no longer confined inside individual neutrons in the usual way. This would be a profound change. The neutron, which seemed like the main character, might itself lose its separate identity. We do not yet know whether this happens inside real neutron stars. That uncertainty is not a gap one can fill by guessing confidently. It depends on the behaviour of matter under conditions that are extraordinarily hard to reproduce and interpret. Observations of heavy neutron stars tell us that whatever is inside must support great pressure. If exotic particles or quark matter appear, they must not soften the matter too much, or the star would collapse into a black hole at masses we know neutron stars can have. Gravitational waves from mergers, X-ray measurements of radii, pulsar timing, and cooling observations all help constrain the possibilities. The core is hidden, but not silent. It leaves clues in the star's mass, size, temperature, spin, and response to tides. There may also be particles called hyperons in the dense core. Hyperons are relatives of protons and neutrons that contain strange quarks. Under extreme density, it may become favourable for some neutrons to convert into these heavier particles. But this creates a puzzle. Hyperons can make dense matter softer, reducing its ability to support a massive neutron star. Yet we observe neutron stars with masses more than twice that of the Sun. This tension is sometimes called the hyperon puzzle. It is a reminder that the interior of a neutron star is not just a place where we can casually add exotic ingredients. Every ingredient changes the pressure, and pressure decides whether the star survives. The star itself is a strict judge. Any theory that cannot hold it up must leave the room. The same is true for other proposed phases. There may be condensates of certain particles, or mixed phases where nuclear matter and quark matter coexist, or colour superconducting quark matter, a state where quarks pair in ways somewhat analogous to electrons in a superconductor. These ideas sound exotic because they are. They belong to a region where particle physics and astrophysics meet under extreme pressure, but they are not fantasy. They are serious possibilities explored through theory and constrained by observation. The difficulty is that neutron stars do not let us take samples. We infer their interiors the way one might infer the contents of a locked room by listening to footsteps, measuring the weight of the building and watching how the walls vibrate when the wind blows. It is impressive work, but the room remains locked. The transformation of matter also affects the star's thermal life. A newborn neutron star is very hot. It cools first by emitting neutrinos from its interior, then later more through radiation from its surface. The particles and phases inside determine how efficiently neutrinos are produced and escape. If certain exotic particles are present, cooling may happen faster. If neutrons and protons form paired states, some cooling processes are suppressed, while others briefly become important. Observing the temperature of neutron stars of different ages can therefore reveal clues about what lies inside. It is a slow, forensic investigation. The star cools, and its cooling curve tells a story about matter that cannot be touched. The loss of atomic shape also changes how the star conducts heat and electricity. The crust, with its lattice of nuclei and sea of electrons, can carry heat in ways that depend on impurities, magnetic fields, and nuclear structure. The core may transport heat through particles moving in superfluid or superconducting states. In magnetars, huge magnetic fields complicate everything, directing heat flow and stressing the crust. This is why two neutron stars of similar age and mass may not look identical. Their magnetic fields, crust composition, accretion history, and internal states can shape their observed behaviour. Matter has forgotten its ordinary shape, but it has not become featureless. It has gained new kinds of structure. There is a quiet danger in saying matter breaks down, because it can sound like matter simply fails. In a neutron star, matter is not failing in a sloppy sense. It is adapting to pressure by finding the lowest energy arrangements available. Atoms collapse because they are no longer stable. Nuclei become neutron-rich because that is favoured under compression. Free neutrons appear because nuclei cannot contain them all. Nuclear shapes form because forces compete. Superfluidity may appear because particles pair. Exotic matter may appear because the chemical balance of the dense interior allows it. This is not disorder in the everyday sense. It is matter obeying rules so deep and strict that ordinary structure cannot survive. Perhaps the most human way to understand it is to think about identity under pressure. A lump of carbon can be graphite or diamond depending on how its atoms are arranged. Heat it, squeeze it, change its environment, and matter takes a different form. A neutron star is the most extreme version of that principle. Hydrogen, helium, carbon, oxygen, silicon, and iron were once part of a massive star's layered life. Then collapse came. The environment changed so violently that the old forms vanished. Matter did not ask what it used to be. It responded to what the pressure demanded. Atoms became irrelevant. Nuclei changed. Neutrons took over. And perhaps, deeper still, even neutrons may surrender their boundaries. That is why neutron stars feel like a threshold. They are not simply heavy balls of stuff. They are places where the definition of stuff becomes conditional. On Earth, matter has shape because atoms have space, and electrons have room to arrange themselves. In a neutron star, gravity removes that room. It squeezes matter until the architecture of atoms collapses and the particles must reorganize. The deeper we go, the more the familiar words become approximations. Solid, liquid, element, molecule, metal, gas, even neutron. Each word works for a while, and then needs careful handling. And this brings us naturally toward the layered interior. The collapse of atoms is not the end of the story. It is the beginning of the star's internal geography. From the thin outer atmosphere to the dense outer crust, from neutron-rich nuclei to free neutron seas, from possible nuclear pasta to the fluid core, a neutron star is arranged by pressure into regions, each stranger than the one above. Matter may have lost its ordinary shape, but it has not lost all structure. It has been reshaped into a series of layers written by gravity, quantum mechanics, and nuclear force. To follow those layers downward is to travel from the last traces of atomic identity into a depth where the surface world has no authority at all. Beneath the surface of a neutron star, the word surface begins to feel a little misleading. On Earth, the surface is a place you can imagine standing. There is ground, perhaps grass, perhaps stone, perhaps a pavement that has seen better days. There is air above and material below, and even if the details vary, the idea is familiar. A neutron star has a surface in the sense that there is an outer boundary from which light can escape into space. But it is not a surface in the friendly sense. It is not a place for footprints, flag planting, or a small scenic cafe with a worrying view. It is the outer skin of one of the densest objects in the universe, a region where gravity has already made ordinary matter nearly unrecognizable, and where the descent inward becomes stranger with every layer. If we could somehow hover above a neutron star safely beyond the reach of its crushing gravity and fierce radiation, we might first notice how small it seems compared with the star it used to be. A sphere perhaps only the width of a city, turning quickly in the dark, carrying more mass than the sun. But that smallness is deceptive. The short distance from surface to center contains a whole sequence of physical worlds. It is not a simple ball of uniform matter. It is layered, not like a planet with rock and metal and molten regions, but like a pressure-written story, each page denser than the one before. The deeper you go, the more the old rules are replaced by new ones. Atoms become distorted, then unstable, then irrelevant. Nuclei are squeezed into unnatural arrangements. Neutrons leak out. Matter forms shapes that sound almost absurd until you remember that the absurdity belongs not to the physics, but to our everyday expectations. The outermost region may be an atmosphere, though that word also needs caution. A neutron star atmosphere is not a gentle blanket of air. It may be extremely thin, perhaps only a short distance thick, held down with such force that even the idea of floating becomes a little ridiculous. Depending on the star's age, temperature, magnetic field, and history, this atmosphere may contain hydrogen, helium, carbon, or heavier elements. If the neutron star has been pulling material from a companion, the atmosphere may be shaped by that incoming matter. If it is isolated, the lightest elements may float upward, while heavier ones sink, sorted by the star's intense gravity. On Earth, a feather and a stone fall differently if air resistance gets involved. On a neutron star, gravity sorts matter with terrifying efficiency. The light elements rise to the top not because they are relaxed, but because everything heavier is being dragged downward with a seriousness that leaves no room for negotiation. This thin atmosphere matters because it is what much of the star's light passes through before reaching us. Astronomers studying neutron stars do not see the interior directly. They see radiation shaped by the surface and atmosphere, bent by gravity, altered by magnetic fields, and filtered by whatever material lies above the crust. A small difference in the atmospheric composition can change how the star's temperature appears from far away. That makes the atmosphere both a clue and a complication. It is like trying to judge the warmth of a room by looking through a fogged window, while the house is spinning rapidly and curving space around itself. Science, as ever, enjoys making the simple things slightly less simple. Below the atmosphere lies the outer crust. This is the first true layer of dense solid material. Though again, solid does not mean what it means in the kitchen or garden. The outer crust is thought to contain atomic nuclei arranged in a crystalline lattice, surrounded by a sea of electrons. These nuclei may begin as familiar kinds of matter, especially near the surface, but under increasing pressure they become more and more neutron-rich. That means they contain far more neutrons than stable nuclei on Earth usually can. In laboratories, extremely neutron-rich nuclei tend to decay quickly. Inside a neutron star crust, the pressure and environment allow them to exist as part of the star's structure. They are not stable because they would be comfortable on Earth. They are stable because the neutron star gives them no better option. The outer crust is only a small fraction of the star's radius, but it is already unimaginably dense by ordinary standards. Still, compared with the deeper layers, it is almost polite. The nuclei remain distinct. The electrons move among them. The material can support shear stress, meaning it can behave like a solid and resist deformation. This crust may be far stronger than any known material on Earth. If you could hold a piece of it, which you absolutely could not, it would not be a mineral, a metal, or a crystal in the everyday sense. It would be a fragment of matter assembled under gravity so intense that Earth materials would seem like loose foam by comparison. As we descend through the outer crust, pressure keeps rising. The electrons are squeezed into higher energy states. The nuclei respond by absorbing electrons through reactions that turn protons into neutrons. This makes the nuclei even more neutron-rich. The elements we know from the periodic table become less useful as familiar identities. The number of protons still matters, but the nuclei are moving far from the stable combinations found in ordinary matter. They are swollen with neutrons, heavy and strange, existing in a narrow balance created by the surrounding pressure. If you were to remove them from the neutron star, they would not remain calmly intact. They belong to this place, and this place only. Then comes a critical boundary, a point where the nuclei can no longer hold all their neutrons. This is the region of neutron drip. The phrase sounds gentle, almost like condensation forming on a cold window, but the reality is a major change in the nature of matter. At this depth, some neutrons are no longer bound inside nuclei. They begin to move freely through the crust, forming a kind of neutron sea around the nuclear clusters. The matter is now made of nuclei, electrons, and free neutrons, all occupying the same compressed environment. The old atomic picture has vanished. Even the nuclear picture is becoming more complicated. This region is called the inner crust. It is one of the most fascinating parts of a neutron star because it is neither the outer crust's more orderly lattice nor the deeper core's more uniform fluid. It is a transition zone, and transition zones in nature are often where interesting things happen. The nuclei become larger, more neutron-rich, and more closely packed. Free neutrons move between them. The electrons continue to provide charge balance. The entire layer is dense, cold in a quantum sense compared with its enormous internal energy, and governed by a mixture of nuclear attraction, electric repulsion, and quantum pressure. It is matter in a state that sounds as if it should have been invented for a thought experiment, except nature has already built it in objects scattered across the galaxy. In the inner crust, the free neutrons may become superfluid. A superfluid is a state of matter that can flow without ordinary viscosity. On Earth, we can create superfluid states in laboratories at extremely low temperatures using helium and other systems. Inside a neutron star, the conditions are entirely different, but the quantum principle of paired particles can still appear. Neutrons may pair up and move collectively in a superfluid state. This does not mean the inner crust is gentle or liquid in any everyday sense. It means part of the matter can move in a way that is not slowed by normal friction. This may be central to understanding pulsar glitches, those sudden tiny speed-ups observed in some rotating neutron stars. The idea is that the crust and the superfluid interior do not always rotate in perfect lockstep. As the neutron star gradually slows down over time, the crust loses rotational energy. The superfluid component may lag behind or store angular momentum in a hidden way. At some point, a sudden transfer occurs, and the crust spins slightly faster. From Earth, astronomers see the pulse timing shift. A star that had been ticking with astonishing regularity suddenly ticks a little differently. That small change may be a message from the inner crust, a signal that the hidden superfluid has moved. It is remarkable, really. We cannot touch the crust. We cannot drill into it. We cannot place instruments on it. But a tiny irregularity in the timing of distant radiation can tell us that the star's interior is not behaving like a simple solid ball. Deeper in the inner crust, the nuclei become so crowded and distorted that they may form the famous nuclear pasta phases. The name is charming enough to almost distract from the severity of the conditions. Physicists use it because the predicted structures resemble familiar shapes, rods, sheets, tubes, and more tangled forms. The comparison is not exact, of course. There is no kitchen, no sauce, no dinner table, and certainly no one asking whether the nuclear lasagna needs more salt. These are arrangements of nuclear matter shaped by the competition between forces. The strong nuclear force favours clumping. Electric repulsion between protons resists too much clumping. The surrounding pressure pushes everything close together. The result may be a series of bizarre structures that minimize energy under those conditions. These pasta phases may be extremely important. They could affect how heat moves through the crust, how neutrinos are emitted, how the crust breaks, and how the star's magnetic field evolves. They may also influence the connection between crust and core. Even if they occupy a relatively thin region, their properties could shape the behavior of the whole star. That is often how neutron stars work. A layer that seems small in size can matter enormously because the densities and forces are so extreme. In ordinary life, a thin layer of frosting on a cake may be important emotionally but not structurally. In a neutron star, a thin layer can alter cooling, cracking, and rotation. The universe has taken the idea of layered dessert and made it deeply serious. At the bottom of the crust, the distinction between nuclei and surrounding neutron matter fades. The nuclear clusters merge into a more uniform phase. This is the transition to the outer core. Here, matter is often described as a dense fluid made mostly of neutrons, with a smaller fraction of protons, electrons, and possibly muons. A muon is a heavier relative of the electron, and under the high energy conditions inside neutron stars, muons can appear as part of the balance of particles. The details depend on density and the dense matter rulebook, but the broad picture is that the core is no longer a lattice of nuclei. It is a fluid of particles packed at and beyond nuclear density. The outer core may make up much of the star's volume and mass. It is not visible, but it dominates the structure. The neutrons there may form a superfluid. The protons may form a superconducting component, meaning they can carry electric currents without ordinary resistance under the right conditions. If this is true, then the magnetic field inside the neutron star is tied to superconducting physics in a dense nuclear fluid. That is a sentence that would be difficult to explain to a medieval astronomer, though to be fair, the medieval astronomer might reasonably ask why we're trying to explain the interior of a dead star at bedtime. Superfluidity and superconductivity are not decorative labels. They change how the star evolves. They affect heat capacity, cooling rates, magnetic field behavior, rotational dynamics, and the way the star responds to disturbances. A normal fluid and a superfluid do not store and transfer motion in the same way. A normal conductor and a superconductor do not handle magnetic fields in the same way. If we want to understand why pulsars glitch, why magnetars flare, why some neutron stars cool faster than others, and how old neutron stars spin for so long with such regularity, we have to care about these hidden states. The layers beneath the surface are not passive. They participate in the star's life. The deeper core is where the uncertainty grows. In less massive neutron stars, the central density may be high, but still within a range where matter can be described mostly as neutrons, protons, electrons and muons interacting through nuclear forces. In more massive neutron stars, the density may become high enough for new particles or new phases of matter to appear. Hyperons may emerge. Meson condensates may form. Quark matter may appear. These possibilities are still debated because the physics is difficult and the observational clues are indirect, but they all share a basic idea. As density rises, matter may lower its energy by changing its composition. The star may open new particle channels, as if pressure is unlocking rooms that ordinary matter never needed to enter. Hyperons are heavier relatives of protons and neutrons. They contain strange quarks, which gives them their name in the family of strange matter possibilities. If hyperons appear in the core, they can change the pressure balance. The trouble is that they may make matter softer, and softer matter has more difficulty supporting massive neutron stars. Since astronomers have measured neutron stars with masses more than twice the Sun's mass, any theory that includes hyperons must still allow the star to hold itself up. This is not a small constraint. A neutron star is a very strict examiner. It does not care if a theory is elegant. If the theory cannot support the observed mass, the theory has a problem. Quark matter is another possibility. Protons and neutrons are made of quarks, but under ordinary conditions those quarks are confined inside the particles. In the deepest core of a massive neutron star, the density may become high enough that the boundaries between individual neutrons overlap and dissolve. Instead of separate neutrons, there might be a state in which quarks move through a larger region. This would mean matter has passed through another level of breakdown. Atoms were lost, nuclei dissolved. Now even neutrons may lose their individual identities. That is one of the reasons neutron star cores are so fascinating. They may contain matter that is not merely compressed, but reorganized at the most basic level accessible outside a black hole. There are even ideas about color superconductivity in quark matter, where quarks pair in special ways. The word color here does not refer to visible color, but to a type of charge in the theory of the strong interaction. Since we are keeping things verbal and gentle, the useful point is this. If quark matter exists, it may not be a simple gas of quarks. It may have its own phases, with its own pairing patterns and transport properties. The core of a neutron star could be not just exotic matter, but exotic matter with structure. The deeper we go, the more the simple phrase dense stuff becomes inadequate. How do we know any of this if we cannot see inside? We combine theory with observation. The mass of a neutron star tells us how much pressure its interior must provide. The radius tells us how compact it is, though radii are difficult to measure. The cooling history tells us how particles inside carry energy away. Pulsar glitches tell us about superfluid components and crust interactions. Magnetar flares tell us about crustal stress and magnetic energy. Gravitational waves from neutron star mergers tell us how deformable the stars are under tidal forces. Each clue is partial, none opens the star completely. But together they narrow the possibilities. It is like reconstructing a hidden instrument by listening to the music it plays, the way it vibrates when struck, and the silence it leaves between notes. The crust and core also communicate. Heat from the core must pass through the crust before escaping. Stress from magnetic fields can move through the crust and affect the surface. Rotational changes may involve coupling between superfluid regions and the solid crust. In young neutron stars, the crust cools and solidifies while the core continues to evolve. In accreting neutron stars, matter falling from a companion can bury the surface, heat the crust, trigger nuclear reactions, and later allow the crust to cool when accretion stops. Astronomers observe these cooling periods to learn about the crust's thermal properties. A neutron star that has fed from a companion can become, in effect, a laboratory for crust physics. Not a comfortable laboratory, but a useful one. Accretion can also replace or alter the outer layers. If material from a companion star falls onto the neutron star, it can accumulate on the surface. Under pressure, this fresh matter undergoes nuclear reactions, sometimes producing bursts of radiation. These bursts can reveal the star's surface gravity, temperature, and composition. The new material is gradually compressed as more arrives above it, sinking into deeper layers and transforming. In this way, the surface of an accreting neutron star is not simply an ancient crust left unchanged since birth. It can be renewed, buried, cooked, and compressed. The star's outer layers remember both its violent formation and its later environment. The magnetic field complicates the layering further. In ordinary stars and planets, magnetic fields can guide charged particles and shape plasma. In neutron stars, magnetic fields can be so strong that they affect atomic structure near the surface and influence heat flow through the crust. Heat may travel more easily along magnetic field lines than across them. This can create hotspots, regions of the surface warmer than others. If the star rotates, these hotspots can produce pulses as they move in and out of view. By studying the pulse shapes, scientists can estimate the star's compactness. But the pulse shape depends on gravity, magnetic field geometry, atmosphere composition, and surface temperature pattern all at once. The neutron star, as usual, does not believe in making interpretation too convenient. In magnetars, the magnetic field may be powerful enough to dominate the behavior of the crust and magnetosphere. Stresses build as the internal magnetic field evolves. The crust may crack or shift. Energy is released into the surrounding magnetic environment, producing bursts or giant flares. Some of the strongest flares observed from magnetars have affected spacecraft detectors across vast distances. A change in a layer only a short distance thick on an object the size of a city can announce itself across the solar system. That is the kind of scaling neutron stars enjoy. Small structure, enormous consequence. As the neutron star ages, its layers continue to change. It cools, it spins down. Its magnetic field may decay or rearrange. The crust may become more stable, but stresses can still build. In isolated stars, the surface grows dimmer. In binary systems, accretion can heat and reshape the outer regions. In merging systems, tidal forces can deform the entire star before collision. The layers are not just static entries in a diagram, they are part of a long evolution. The neutron star is born hot and turbulent, settles into structure, and then spends its life slowly revealing that structure through timing, light, bursts, and gravitational waves. There is something almost planetary about discussing layers, but we should not let that comparison carry us too far. Earth's layers are made of rock, metal, liquid, and solid phases under high pressure and temperature. A neutron star's layers are made of nuclear matter, quantum fluids, superconducting components, and possible exotic particles. Earth's core is difficult to reach, A neutron star's core is impossible in a much deeper sense. Earthquakes allow us to study our planet's interior through seismic waves. Neutron stars may have oscillations too, and scientists hope to use bursts, flares, and gravitational waves to study their internal vibrations. This is sometimes called a kind of stellar seismology. The idea is similar in spirit. Listen to how the object rings and infer what lies inside. But the instrument is not rock. It is compressed nuclear matter held together by gravity near the edge of collapse. A layered neutron star is also a reminder that nature does not need large distances to create complexity. The journey from atmosphere to inner core may cover only a dozen kilometers or so, perhaps a bit more depending on the star. On Earth, that is a commute. Inside a neutron star, it is a passage from recognizable nuclei to neutron seas, nuclear pasta, quantum fluids, and unknown core matter. Each kilometer matters. Each increase in pressure can change the preferred state of matter. The object is small enough to fit over a city, but its interior is rich enough to challenge nuclear physics, astrophysics, and relativity all at once. So when we speak of the strange layers beneath the surface, we are really speaking of matter being sorted by pressure into a sequence of increasingly unfamiliar forms. A thin atmosphere clings to the outside. A solid outer crust holds neutron-rich nuclei in a lattice. An inner crust contains free neutrons and perhaps superfluid behavior. Near the base, nuclear matter may stretch into rods, sheets, and other pasta-like structures. The outer core becomes a dense fluid of mostly neutrons with other particles mixed in. The deeper core may contain particles and phases that remain uncertain. Every layer exists because gravity presses inward, and quantum physics answers back. And that answer grows less certain toward the center. The crust, strange as it is, still gives us some handles. We can imagine nuclei, electrons, free neutrons, lattices, and transitions. The outer core is harder, but still within a broad nuclear picture. The inner core is where the language begins to fray, is where the star may stop being mostly a neutron star in the simple sense and become something more difficult to name. The deeper we go, the more the question changes from how is matter arranged to what counts as matter here at all. The surface has led us to the crust to the core, and the core now asks us to consider whether the particles we have relied on are still the right ones. At the centre of a neutron star, the language of ordinary matter begins to run out of breath. Near the surface, we can still speak with some confidence about nuclei, electrons, and crusts. Deeper down, we can talk about neutron-rich matter, free neutrons, superfluids, and dense fluids. These ideas are strange, but they are still connected to things we understand through nuclear physics and quantum mechanics. But as we approach the core, especially the deepest region of a massive neutron star, the question becomes less comfortable. It is no longer only a matter of how tightly neutrons are packed. It becomes a question of whether neutrons are still the right things to talk about at all. This is where neutron stars become more than compact remnants. They become places where physics itself is tested at the edge of its current reach. Not broken in the sense that the universe stops obeying rules. The universe is not sitting there in the core of a neutron star shrugging and saying, "Well, I suppose we shall improvise." It is obeying rules exactly. The difficulty is that we do not yet know all the rules well enough in this regime. The density is too high, the pressure too intense, the particles too crowded, and the conditions too far from anything we can reproduce steadily in a laboratory. We have theories, observations, computer models, and clever indirect tests, but the center of a neutron star remains hidden. And hidden things tend to make physicists both nervous and excited, which is essentially the professional condition of physics. Let us begin with the simplest picture, and then let it become more complicated. A neutron star is often described as a giant atomic nucleus, a huge ball of neutrons packed together at nuclear density. This picture is useful for a first step. It captures the idea that the star is not made of ordinary atoms, and that neutrons dominate much of its mass. But it is also misleading if taken too literally. An atomic nucleus is held together by the strong nuclear force over tiny distances. A neutron star is held together by gravity over a distance comparable to a city. It has layers, pressure gradients, rotation, magnetic fields, and particle mixtures. It is not one enormous nucleus in the simple sense. It is a gravitational object made of matter at and beyond nuclear density, and that distinction matters. In the outer core, the matter may be mostly neutrons, with a smaller fraction of protons, electrons, and muons. These particles are packed into a dense quantum fluid. The neutrons may be superfluid, the protons may be superconducting. Electrons and muons help maintain charge balance and participate in transport of heat and electric current. This is already far from normal matter, but physicists can describe it with extensions of nuclear theory. The interactions between neutrons and protons are difficult, yes, but they are tied to physics we can study in nuclei and particle experiments. The outer core is mysterious, but not completely alien. The inner core is another matter. In a low-mass neutron star, there may not be much of an inner core in the exotic sense. The central density may remain within a range where nucleons, meaning protons and neutrons, still dominate. But in heavier neutron stars, the pressure at the center can become so great that new possibilities open. The star may find it energetically favorable to create particles that are not present in ordinary matter. It may allow neutrons to convert into heavier relatives. It may dissolve the boundaries between particles. It may form phases of matter that we have named but not directly held. The trouble is that each of these possibilities changes the pressure inside the star, and pressure is what keeps the star from collapsing. So every new ingredient must pass a very strict test. Can it appear without making the star too soft to survive? Softness here does not mean squishiness in the everyday sense. No one is pressing the core of a neutron star with a thumb, and if they were, the thumb would have several urgent complaints. In dense matter physics, softness means that pressure does not increase enough as density rises. A softer core is more compressible. A stiffer core resists compression more strongly. This matters because we have observed neutron stars with more than twice the mass of the Sun. Any proposed interior must support such massive objects. If a model says that exotic particles appear, but their appearance reduces pressure so much that the star collapses at a lower mass than we observe, then the model is in trouble. The star itself becomes evidence. It says, whatever is happening inside me, it must be strong enough to hold me up. One possibility is the appearance of hyperons. Hyperons are particles related to protons and neutrons, but heavier and containing a type of quark not usually present in ordinary matter. In the high-density core, forming hyperons may become favourable because it can lower the energy of the system. That sounds reasonable, but it creates a problem. When hyperons appear, they often soften the matter. That makes it harder to support a very massive neutron star. This tension is known as the hyperon puzzle. It is not a puzzle in the sense of a crossword tucked into a Sunday newspaper, though one imagines physicists might appreciate a version with fewer missing experimental constraints. It is a serious problem about how dense matter can include these particles and still remain stiff enough to match what astronomers observe. There are ways to try to solve it. The interactions between hyperons and other particles may be more repulsive at high density than simple models suggest. Additional forces may stiffen the matter again. Hyperons may appear only at densities reached in some stars but not others. Or perhaps they do not appear at all in the stars we have observed. The point is that the core is a place where particle physics and astronomy argue through evidence. Particle theory says these ingredients may be possible. Stellar observations say, only if they do not ruin the structure. Somewhere between the two lies the truth. Another possibility is the formation of meson condensates. Mesons are particles made from quark and antiquark pairs. Under certain dense conditions, some theories suggest that particular mesons could form collective states in the core. These states could alter the pressure, cooling, and composition of the star. Again, the same difficulty appears. If such condensates soften matter too much, They may conflict with heavy neutron star observations. If their interactions are different, or if they appear only under certain conditions, they remain possible. The inner core is not generous with certainty. It lets ideas approach, then asks whether they can carry a star. Then there is quark matter, perhaps the most famous possibility. Protons and neutrons are not fundamental particles. Each is made of quarks bound together by the strong interaction. Under ordinary conditions, quarks are confined. They do not wander freely through space. If you break a proton apart in a high-energy experiment, you do not simply get isolated quarks drifting away like peas from a pod. The strong force behaves in a way that keeps quarks bound into particles. But at extremely high density, when neutrons and protons are packed so closely that their boundaries overlap, some theories suggest that quarks may no longer remain confined inside individual particles. Instead, matter may become a form of quark matter, where quarks move through a larger region as the relevant degrees of freedom. That phrase sounds technical, so let us make it gentler. Imagine a room full of people each sitting in their own chair with clear space between them. You can identify each person and each chair. Now imagine the room being packed tighter and tighter until the chairs overlap. The boundaries between personal spaces vanish, and it no longer makes sense to describe the room as separate seated individuals. The people are still there, in some sense, but the arrangement has changed so much that a new description is needed. In dense matter, neutrons may reach a point where their internal quark structure can no longer be treated as sealed away inside separate particles. The matter may need to be described in terms of quarks themselves. Would that mean the neutron star has a quark core? Possibly. Some models allow a transition from nuclear matter to quark matter in the deepest region. Others suggest a mixed phase where nuclear matter and quark matter coexist over a range of densities. Still others suggest that quark matter, if it appears, might be arranged in special paired states. One such possibility is colour superconductivity. The word colour here is not about red, blue or green light. It refers to a kind of charge in the theory of the strong interaction. In these phases, quarks may pair up in ways that change the properties of the matter, somewhat like electrons pairing in an ordinary superconductor, though under conditions that make ordinary superconductors look like a quiet hobby project. If quark matter exists in neutron star cores, it could affect many observable properties. It might change the star's radius for a given mass. It might alter how the star cools by changing neutrino emission. It might influence the behavior of mergers and the gravitational waves they produce. It might even lead to a distinct family of compact stars, sometimes called hybrid stars, with nuclear matter outside and quark matter inside. Some speculative ideas go further, imagining strange quark stars made almost entirely of strange quark matter, but those ideas remain uncertain. The difficulty is not that scientists lack imagination. The difficulty is that nature has to agree. One of the central challenges is the behavior of the strong interaction at high density. The strong interaction is well understood in some regimes, especially at very high energies where certain mathematical simplifications help, and in ordinary nuclei where experiments provide guidance. But cold, ultra-dense matter like that inside neutron stars sits in a difficult middle ground. It is not easy to calculate directly from the underlying theory. Models must make approximations. Different approaches can give different answers. This is why observations are so valuable. They narrow the allowed possibilities. A heavy neutron star rules out interiors that collapse too easily. A radius measurement constrains how stiff the matter is. A gravitational wave signal from a merger tells us how easily the star deforms. A cooling curve may hint at which particles carry energy away. This is one of the most elegant things about neutron star science. The interior is invisible, but not unreachable. We cannot look into the core, but the core influences the whole star. It determines the relationship between mass and radius. It affects how the star responds to tides. It shapes how heat leaves the interior. It may influence rotational glitches. It controls the maximum mass before collapse to a black hole. The core writes its signature on the outside, but in a code that requires patience to read. Astronomers gather the signals, nuclear physicists build the models, relativists calculate how gravity bends the evidence, then everyone compares notes, and, ideally, no one spills coffee on the data. The maximum mass is especially important. A neutron star survives only if its internal pressure can balance gravity. Add too much mass, and the balance fails. The star collapses into a black hole. The precise maximum mass depends on the dense matter equation of state, the rule describing how pressure responds to density. Observing very massive neutron stars tells us the rule must be stiff enough at high density to support them. But gravitational wave observations of neutron star mergers suggest that neutron stars cannot be too large or too stiff, because their tidal deformability would then be greater than what is observed. So matter must be stiff enough to hold up heavy stars, but not so stiff that stars become too large or too easily deformed. It is a narrow path. Dense matter must walk it carefully, though dense matter has no feet and very little concern for metaphors. The core may also contain superfluid phases. We mentioned superfluid neutrons in the crust and outer core, but deeper inside, pairing patterns may change with density. Particles can pair in different ways depending on their energies and interactions. These paired states affect heat capacity and neutrino emission. When particles pair, some processes that would normally cool the star are suppressed, while other processes connected to the formation and breaking of pairs can occur. This makes the thermal evolution of neutron stars a sensitive probe of internal physics. A young neutron star cooling over decades or centuries can reveal whether certain particles are paired, whether fast cooling processes operate, and whether exotic matter might be present. The star's temperature becomes a kind of diary of its hidden core. One famous example often discussed is the neutron star in the Cassiopeia, a supernova remnant. Observations suggested it may have cooled measurably over a short period, though the interpretation has been debated. Some models connected this cooling to the onset of neutron superfluidity in the core. The details are still not settled, but the idea shows how subtle the clues can be. A slight change in X-ray temperature, measured from a compact object thousands of light years away, may tell us about particle pairing in matter denser than an atomic nucleus. That is the kind of detective work neutron stars demand. Nothing is close, nothing is easy, and yet the clues are real. Rotation gives another set of clues. Pulsars can be timed with astonishing precision. Some rotate hundreds of times per second. Their stability tells us about the distribution of mass and the coupling between crust and core. Their glitches suggest that superfluid components store and release angular momentum. Their spin limits constrain the radius and internal structure. A neutron star spinning too fast would break apart if it were too large or insufficiently bound. So the fastest pulsars are not just impressive clocks, they are tests of dense matter. Every pulse says, "I am still here, still rotating, still not flying apart, so your theory had better allow that." Magnetic fields complicate the core further. In ordinary neutron stars, the magnetic field may already be enormous. In magnetars, it is extreme. The field may thread the crust and core, interacting with superconducting protons or other charged components. If the core is superconducting, magnetic flux may be arranged in tiny quantized tubes. These structures can interact with superfluid vortices associated with rotation. The words are technical, but the physical point is that the interior may contain a hidden tangle of rotational and magnetic structures. Changes in this hidden arrangement could influence the crust, the spin, and the flares we observe. A magnetar outburst may begin with stresses built deep inside, transferred outward through layers that we can only model. It is not simply a surface event. It may be the visible end of a long internal argument. At the highest densities, the core may also challenge the boundary between a neutron star and a black hole. A neutron star is stable because pressure balances gravity. But if the core becomes too soft, or if the star gains mass from a companion, or if two neutron stars merge, the balance can fail. In a merger, The remnant may briefly be a hypermassive neutron star supported temporarily by rapid rotation and thermal pressure. Then it may collapse to a black hole. The time before collapse depends on the dense matter equation of state. If gravitational waves or electromagnetic signals reveal how long the remnant survived, they can tell us about the stiffness of the core. A core's hidden physics can decide whether the final object remains visible for a moment or vanishes behind an event horizon. This is where the phrase physics begins to fray needs care. Physics itself is not failing. Our descriptions are. The known theories do not stop working in a dramatic puff of chalk dust. General relativity describes gravity very well at neutron star scales. Quantum mechanics and nuclear physics describe matter, though with difficulty at these densities. The problem is that combining all the relevant ingredients under these conditions is hard. The calculations are uncertain, the experiments are indirect, the observations are improving, but not yet decisive. The fraying is in our map, not necessarily in the territory. The neutron star core is not lawless. It is simply governed by laws we have not fully translated into practical predictions. That uncertainty is important to preserve. It would be easy, and rather tempting, to say the core definitely contains quark matter, or definitely contains hyperons, or definitely remains ordinary nuclear matter all the way down. But the honest answer is more measured. The core may contain exotic particles or phases, especially in massive neutron stars. It may undergo transitions that change the behavior of matter. It may remain nucleonic in some stars and become more exotic in others. The evidence is still being gathered. In science, not knowing is not a weakness when the not knowing is precise. It tells us where to look. Modern instruments are making that search sharper. X-ray telescopes can study hotspots on rotating neutron stars, using pulse shapes to infer mass and radius. Radio telescopes time pulses and measure masses in binary systems. Gravitational wave detectors listen for neutron star mergers and extract tidal information from the signal. Optical and infrared telescopes study the glow from merger debris, which reveals how matter is ejected and what elements are formed. Each method approaches the core from a different angle. None is enough alone. Together they are beginning to squeeze the possibilities, which seems appropriate since squeezing is the neutron star's main theme. Laboratory experiments also help, though they cannot make neutron star matter in the full sense. Heavy ion collisions can create hot, dense nuclear matter for tiny fractions of time. Nuclear experiments can measure properties of neutron-rich nuclei. Theory and computation connect these results to astrophysical conditions. The laboratory gives pieces of the puzzle. The star gives others. The two must meet carefully because neutron star cores are cold and dense compared with many collision experiments, which are hot and fleeting. Still, every constraint matters. The core is too remote for direct access, so scientists build a net from many kinds of evidence. There is also a philosophical quietness in all this, though we need not drift too far into it. A neutron star core reminds us that matter is not a single familiar thing, it is conditional. Under one set of conditions, matter makes atoms, molecules, oceans, skin, clouds, and tea. Under another, it becomes plasma in a star. Under another, it becomes the electron-supported matter of a white dwarf. Under another, it becomes neutron-rich nuclear matter. Under still greater pressure, it may become something where even protons and neutrons are no longer the best description. The identity of matter depends on the environment. The universe does not promise that the categories useful in a living room will remain useful at the centre of a collapsed star. And yet the core is not separate from us in a cosmic sense. The same particles, forces, and rules are involved. The neutrons in the star are not magical objects from another universe. The quarks, if freed into quark matter, are the same kinds of ingredients that build ordinary protons and neutrons. The physics is unfamiliar because the conditions are unfamiliar, not because the star is made of something outside nature. That is comforting in a scientific way. The core is alien, but not supernatural. It is a place where the ordinary rules are pushed into extraordinary consequences. so we arrive at a picture that is both specific and incomplete. The outer parts of a neutron star give way to a dense core made mostly of neutrons and other particles. In the deepest regions, especially in massive stars, new particles may appear, hyperons may enter, meson condensates may form, quark matter may emerge, pairing and superfluidity may change the star's cooling and rotation. The matter must remain stiff enough to support heavy neutron stars, but not so stiff that it conflicts with observed radii and tidal behaviour. The star is a balance between gravity's demand and matter's answer, and the core is where that answer is hardest to hear. What makes this especially fascinating is that the core controls the fate of the whole object. It helps decide how large the star is, how massive it can become, how it cools, how it rings, how it merges, and when it collapses. A region we cannot see directly governs the visible behaviour of one of the universe's most extreme objects. That is often how deep physics works. The hidden structure shapes the observable world. We infer the unseen not because we enjoy mystery for its own sake, although admittedly we do, but because the surface cannot be fully understood without the depths. For now, let the image settle without forcing it to become too neat. A neutron star's core is not a simple ball of neutrons, nor is it certainly a sea of free quarks. It is a dense, pressured quantum region where several possibilities compete. It may be different from star to star. A lighter neutron star may have one kind of core, while a heavier one may cross thresholds into new phases. The universe may not have chosen one answer for all neutron stars. It may have built a family of objects whose interiors change with mass, age, rotation, and history. That would be inconvenient for tidy diagrams, but the universe has never been especially committed to tidy diagrams. The closer we look, the more neutron stars become instruments rather than just objects. They measure the behaviour of matter by existing. Their masses test pressure, their radii test stiffness, their mergers test deformability, their cooling test particle processes, their glitches test superfluid dynamics, their flares test crust and magnetic fields. The core is hidden, but the star as a whole keeps reporting on it, pulse by pulse, burst by burst, ripple by ripple, and from here the story begins to widen again. We have followed the matter inward, from the surface to the crust, from the crust to the core, and from neutrons toward the possibility of stranger phases. But neutron stars do not keep all their secrets locked inside. They speak through light, through radio pulses, through X-rays, through sudden flares, through gravitational waves, and through the heavy elements scattered when they collide. To understand these objects fully, we have to listen to the signals they send across space, because the dark heart of a neutron star is not entirely silent. It is hidden, yes, but it turns, cools, cracks, merges, and leaves traces that the universe carries outward for anyone patient enough to receive them. A neutron star cannot be visited, touched, sampled, or opened. It does not allow a spacecraft to land gently on its surface, unfold a little ramp, and send out a rover with a camera and a cheerful sense of purpose. It does not offer rocks to collect, soil to scoop, or weather reports to compare with home. It is too compact, too hot when young, too magnetic in some cases, too gravitationally severe in all cases, and yet, for something so inaccessible, it is surprisingly talkative. Not in words, of course. A neutron star does not lean across the galaxy and say, "Good evening, I contain superfluid neutrons and possibly quark matter, do make yourself comfortable." But it sends signals, it pulses, it glows, it flares, it tugs on companions, it shakes space-time when it merges with another dense remnant. It leaves patterns in light and gravity that carry information across thousands or millions of years, arriving at our instruments as faint clues from a place no instrument could survive. This is how we listen to the dark heart of the universe. Not by going there, but by learning how extreme objects announce themselves. A neutron star is hidden in one sense because its deepest interior is sealed behind layers of matter and crushing gravity. But it is not silent. Every rotation, every burst, every change in temperature, every tiny irregularity in a pulsar rhythm, every ripple from a merger carries some part of the story. The challenge is that the story is written in a language of radiation, timing, spectra, and gravitational waves. We do not hear it with ears. We hear it with radio telescopes, X-ray observatories, gamma-ray detectors, optical telescopes, neutrino detectors, and gravitational wave interferometers. The universe is not quiet. We simply had to build enough kinds of listening devices. The first great surprise came from pulsars. In the late 1960s, astronomers detected radio signals arriving with astonishing regularity. Pulse after pulse, steady as a clock, from a point in the sky. At first, the regularity was so striking that the source was jokingly given a name that suggested little green men. That was not because scientists had abandoned caution. It was because when the universe taps out a signal with that kind of precision, one is allowed at least a brief raised eyebrow. The real explanation turned out to be just as wonderful, and in some ways stranger. The pulses came from rapidly spinning neutron stars. Their magnetic fields guide beams of radiation outward, and as the star rotates, those beams sweep across space. If Earth lies in the path, we see a pulse each time the beam points toward us. A lighthouse is the usual comparison, and it is a good one, though most lighthouses are not made from collapsed stellar cores rotating many times per second. Pulsars change neutron stars from theoretical remnants into observable clocks. Their timing can be incredibly precise. A pulse arrives, then another, and astronomers can predict the pattern with extraordinary accuracy. But the small deviations are just as important as the regularity. Some pulsars gradually slow down because they lose rotational energy. Some suddenly glitch, spinning a little faster in a tiny jump before settling again. These glitches are among the clues that the interior is not a simple rigid ball. They suggest that superfluid matter inside the star can store and release angular momentum, exchanging it with the crust. A tiny shift in timing measured from Earth becomes evidence for hidden motion in matter denser than an atomic nucleus. It is a little like listening to a clock in another country and inferring that something inside one of its gears is made of ghostly liquid. Not an everyday hobby, perhaps, but astronomy has always rewarded patience. Pulsars also help us test gravity. When a pulsar orbits another star, especially another compact object, the timing of its pulses changes as it moves around the orbit. Those changes can reveal the masses of the objects, the shape of the orbit, and the effects of relativity. In some binary pulsar systems, the orbit slowly shrinks because energy is carried away by gravitational waves. Long before gravitational waves were directly detected on Earth, binary pulsars gave strong indirect evidence that such waves were real. A spinning neutron star became a clock placed in a gravitational laboratory built by nature. That is a generous thing for a dead star to do, really. It explodes, collapses, spins, and then helps confirm one of the deepest predictions of modern physics. Radio pulses are only one voice. Neutron stars also speak in X-rays. Young neutron stars are hot, and their surfaces can glow strongly at high energies. Some have hot spots near their magnetic poles. As the star rotates, those hot spots move in and out of view, producing changing X-ray brightness. By studying the shapes of these pulses, scientists can estimate the mass and radius of the star. This is not simple, because gravity bends the light, the atmosphere changes the radiation, and the star may rotate rapidly. But precisely because the light is bent by gravity, it carries information about compactness. The pulse shape tells us how much of the surface is visible, how strong the gravity is, and how the star is oriented. The neutron star is difficult to interpret, yes, but it cannot help leaving fingerprints on its own light. Mass and radius matter because they point toward the interior. A neutron star with a certain mass and a certain radius tells us how stiff or soft the dense matter must be. If the star is small for its mass, the matter may be more compressible. If it is larger, the matter may resist compression more strongly. Observing several neutron stars helps narrow the possible rulebook for dense matter. This rulebook is what decides whether the core contains mostly neutrons or hyperons, or quark matter, or some mixture we have not yet fully understood. In this way, light from a hotspot on the surface can become a clue about the hidden state of matter at the centre. The surface speaks for the core, though perhaps reluctantly and with a strong accent. Some neutron stars are louder than others. Magnetars are neutron stars with extremely strong magnetic fields, and they can produce powerful bursts and flares. A magnetar may sit quietly for years, then suddenly release a blast of high-energy radiation. The cause is thought to involve stress in the crust and changes in the magnetic field. The crust, though thin compared with the star as a whole, is under enormous strain. The magnetic field can twist and shift, storing energy. When the crust cracks, or the magnetic environment rearranges, energy is released. A magnetar flare can be detected across vast distances. A small object barely wider than a city can make itself known across the galaxy. That is one of the recurring lessons here. Neutron stars are small only in size. In consequence, they are anything but small. These bursts may also make the star ring. Just as earthquakes can make Earth vibrate, starquakes can set up oscillations in a neutron star. If those vibrations appear in the fading light after a flare, they may reveal properties of the crust and interior. This is a kind of seismology, though the ground is nuclear matter and the instrument is a high-energy telescope. On Earth, seismic waves reveal the mantle and core. In neutron stars, oscillations may someday reveal the crust thickness, magnetic field structure, and internal composition. The idea is wonderfully direct in principle. Strike the object, listen to how it rings, and infer what it is made of. The difficulty is that the object is thousands of light years away. The ringing is faint, and the bell is made of matter that has forgotten how to be atoms. Then there are neutron stars that feed. In binary systems, a neutron star can pull gas from a companion star. The gas spirals inward, forming a hot disk, and eventually falls onto the neutron star surface or along magnetic field lines. The energy released is enormous. These accreting neutron stars can shine brightly in X-rays. Sometimes material builds up on the surface until nuclear burning ignites in a sudden flash, producing an X-ray burst. These bursts are not only spectacular, they are diagnostic. Their brightness, cooling, and repetition can tell us about surface gravity, composition, and radius. The falling matter also heats the crust. When accretion pauses, the crust cools, and astronomers can watch the cooling over time. That cooling reveals how well heat moves through the crust, and how the crust is connected to the core. A neutron star that has been fed by a companion becomes, in a strange way, an experiment in thermal physics. The companion supplies material, gravity supplies pressure, and astronomers supply careful weighting. Cooling is one of the quietest signals, but also one of the most important. A neutron star is born incredibly hot, then cools over time. At first, much of the cooling happens through neutrinos escaping from the interior. Later, surface radiation becomes more important. The rate of cooling depends on what particles exist inside and how they interact. If certain fast neutrino processes are allowed, the star can cool rapidly. If particles form superfluid or superconducting states, cooling may be slowed or altered in distinctive ways. Exotic matter in the core could change the cooling pattern, so the temperature of a neutron star, measured at different ages, becomes a clue about the interior. It is a slow message, written over centuries or millennia. Not all cosmic signals arrive as dramatic flashes. Some arrive as a fading warmth. The most dramatic listening of all comes from gravitational waves. When two neutron stars orbit each other, they gradually spiral inward, losing energy as ripples in space-time. In the final moments, their orbit speeds up, the waves grow stronger, and the stars distort each other through tidal forces. Then they merge. For the first time in human history, we have detected gravitational waves from such a merger and seen light from the same event. That was a turning point. It showed that neutron-star collisions are not just sources of gravitational waves, but also sites where heavy elements can form and be scattered into space. The glow after the merger revealed material rich in newly made elements. Gold, platinum, and other heavy nuclei can be forged in these violent environments. The dark hearts of dead stars collide, and the universe makes treasure. It sounds like myth, but it is physics. The gravitational waves from a neutron star merger carry information from the final dance before contact. The stars are not perfectly rigid. Each one is stretched by the gravity of the other. How much it stretches depends on its internal structure. A larger, softer, more deformable star leaves a different imprint than a smaller, more compact one. By measuring that imprint, scientists can infer properties of dense matter. This is one of the most beautiful parts of the story. The interior of a neutron star affects the shape of space-time waves sent out before the stars even touch. Matter hidden beneath a surface no one can visit leaves its mark on the universe itself. After the merger, several things can happen. The combined remnant may collapse quickly into a black hole. It may survive briefly as a hypermassive neutron star supported by rapid rotation and heat. It may last longer before collapsing, or in some cases perhaps remain as a very massive neutron star if the total mass is low enough. The exact outcome depends on the mass and the dense matter rulebook. Signals after the merger, including gravitational waves, gamma rays, X-rays, radio emission, and optical light, can reveal what happened. The short burst of gamma rays tells us about jets and compact object formation. The longer glow tells us about ejected matter and radioactive decay of newly formed elements. The late radio emission can trace material ploughing into surrounding space. Each signal is one instrument in a cosmic orchestra, though the orchestra is extremely far away and has a habit of performing only when it feels like it. Neutrinos may also carry information from neutron stars and supernovae. During the collapse of a massive star, vast numbers of neutrinos escape from the forming neutron star. Detecting neutrinos from a nearby supernova gave scientists a direct glimpse into the core collapse process. If another nearby supernova occurs, modern detectors could collect far more neutrino data, revealing details about the birth of a neutron star in real time. Neutrinos are difficult to catch because they interact so weakly, but that weakness is also what makes them valuable. They can escape from regions light cannot easily leave. They're ghost messengers from deep inside the event. If light is a postcard from the surface, neutrinos are a hurried note slipped out from the core. There is also the possibility of continuous gravitational waves from isolated spinning neutron stars. If a neutron star has a tiny deformation, a small mountain or internal asymmetry, and if it spins rapidly, it may emit faint gravitational waves continuously. Detecting these would be difficult, but they would tell us about the strength of the crust and the star's internal structure. How tall a mountain can a neutron star support? How uneven can it be while spinning? These sound almost quaint questions until we remember that a mountain on a neutron star may be only a few millimeters high and still represent an enormous mass. The search itself is a way of asking how strong nuclear crust can be under gravity that flattens nearly everything. All of these listening methods share one theme. The neutron star is not understood through a single window. It must be studied through many messengers. Radio pulses reveal rotation and timing. X-rays reveal surface heat, hotspots, bursts, and accretion. Gamma rays reveal magnetar flares and merger jets. Optical and infrared light reveal expanding merger debris and heavy element formation. Neutrinos reveal collapse and cooling processes. Gravitational waves reveal mass, motion, deformation, and mergers. This is called multi-messenger astronomy. though the phrase sounds almost too neat for something so grand. It means the universe is sending information in several forms at once, and we've begun learning how to combine them. The result is that neutron stars are no longer only theoretical curiosities. They are measured objects. We know some of their masses with remarkable precision. We are improving radius estimates. We have observed pulsar glitches, magnetar flares, X-ray bursts, cooling neutron stars, accreting systems, binary and spirals, and merger afterglows. Each observation reduces the space of possible interiors. Each new detection asks the dense matter rulebook to be a little more specific. The answer is not complete yet. We still do not know whether quark matter exists in the core of some neutron stars. We still debate the role of hyperons, condensates, superfluid phases, and magnetic structures. But the questions are becoming sharper. Science often advances not by suddenly knowing everything, but by learning exactly what it does not know. There is something calming about that in a way. A neutron star is extreme beyond imagination, but our approach to it is careful, patient, and cumulative. We do not conquer it. We listen. We compare signals. We refine models. We admit uncertainty. We wait for the next pulse, the next burst, the next merger, the next faint clue. The object itself may be violent, but the science is often quiet. A radio dish turns slowly under the night sky. A detector arm measures a shift smaller than an atomic nucleus. A telescope counts X-ray photons from a hotspot on a star that collapsed before human history began. A researcher checks a timing residual and notices that the pulse arrived a little early. From these small acts of attention, we learn about the densest matter we can observe, and perhaps this is the right place to remember what we have followed. A giant star lived fast and died violently. Its core collapsed when fusion could no longer hold gravity back. Electrons and protons were pressed into neutrons. The outer layers exploded into space, enriching the galaxy, while the core survived as a compact remnant. That remnant is small enough to fit across a city, yet massive enough to bend light and slow time. Its crust contains matter stranger than any mineral. Its inner layers may hold superfluid neutrons, superconducting protons, nuclear pasta, and perhaps deeper phases we have not yet confirmed. Its core may be mostly nuclear matter, or it may contain hyperons, quark matter, or something else that waits behind the limits of our current understanding. All of this is hidden, and yet not unreachable, because the star keeps sending out clues. There is a lovely contrast here. A neutron star is one of the most hostile places in the universe, but it teaches through gentleness at a distance. A pulse arrives softly at a receiver. A point of X-ray light changes brightness. A gravitational wave passes through Earth so faintly that only the most sensitive instruments can notice. The original events are enormous, but the signals that reach us are delicate. Astronomy is often the art of treating delicate signals with enough respect that they reveal violent truths. So when we say we are listening to the dark heart of the universe, we are not only speaking of neutron stars themselves, we are speaking of the method. The universe does not always show its deepest workings directly. Black holes hide behind horizons. Neutron star cores hide beneath nuclear matter. The early moments of explosions are wrapped in dense stellar material. But the hidden world leaves traces. It changes timing. It changes light. It changes waves. It changes the elements scattered into space. To listen is to understand that the unseen is not necessarily unknowable. And now, as this quiet journey through crushed stars and dense matter begins to settle, you might picture a neutron star far away in the dark, spinning with impossible steadiness. Perhaps it is a pulsar sweeping a beam through space like a lighthouse for no ocean. Perhaps it is a magnetar waiting through long silence before a sudden flare. Perhaps it is locked in orbit with another neutron star, slowly spiraling toward a future collision that will shake space-time and scatter heavy elements into the galaxy. Or perhaps it is old and cooling, dim, almost invisible. carrying its secrets in silence until some future instrument learns to hear more. Wherever you are listening from tonight, under whatever sky is above you, the universe is full of these hidden remnants. They are the compact memories of massive stars, the places where matter has been pressed to the edge of what it can be, the laboratories nature built when gravity became stronger than starlight, and although we cannot travel to them, we can receive them. Pulse by pulse, flare by flare, ripple by ripple. A neutron star is not only a dead star, it is a message sent through darkness, telling us that matter is deeper than our everyday world suggests, and that even after a star dies, its core may keep speaking for millions of years. If this journey has brought you a little calm, or a little wonder, or simply given your thoughts somewhere vast and quiet to wander, then I would be very grateful if you liked the video and subscribed. It helps this peaceful corner of physics reach others who might enjoy drifting through the universe at a slower pace. And if you are still awake, that is all right. Some questions are worth carrying gently for a while before sleep arrives, so let the image fade slowly. The city-sized star in the dark, the crust under strain, the core beyond certainty, the pulses crossing space, the detectors waiting patiently here on Earth. Somewhere, a neutron star turns, and somewhere else, a listener rests beneath a much gentler gravity. Sleep well, fellow traveller, and may your own night be softer than the surface of a neutron star,